Dear students, now let us discuss the detailed solutions for the most important unit, that is air cycles or air standard cycles or gas power cycles. Okay, look at the very first question asked in the year 1996 for 1 mark. It is given like this: a cycle consisting of two reversible isothermal process and two reversible isobaric process is known as Atkinson cycle. You know, Atkinson cycle consists of two reversible adiabatic process, one constant volume heat supplied process, one constant pressure heat rejection process. Next, Stirling cycle consists of two isothermal process, two isochoric process, two constant volume process. Brayton cycle consists of two reversible adiabatic process, and two isobaric process, two constant pressure process. Whereas the erection cycle consisting of two isothermal process, two constant pressure process. It is asked for the cycle with two isothermal and two isobaric. Two isothermal, two isobaric is the erection cycle. Therefore, option D is absolutely correct. Understood clearly? Yes. Then the erection cycle in the PV diagram can be marked like this: pressure versus volume diagram. It consists of isothermal compression. This may be the representation of isothermal compression, followed by constant pressure heat addition, followed by isothermal expansion, followed by constant pressure heat rejection process. That is the representation of erection cycle. Temperature constant, pressure constant, okay, that is the erection cycle with the PV diagram. Understood clearly? Yes. Then look at the 2 marks questions asking like this. It is asked in the year 89 before 90. It is like this: in air standard Otto cycle, the terminal pressures, in air standard Otto cycle, the terminal pressures at the end of compression, heat release and expansion are respectively P2, P3 and P4. The pressure after compression P2, pressure after heat release means heat supplied P3, pressure after expansion P4. If the corresponding values are P2 dash, P3 dash and P4 dash, taking into account the effect of variable specific heat and dissociation of the working fluid. Dissociation, association means like it is like this: C plus O2, C is combining with oxygen to produce carbon dioxide, that is called association. But if the CO2 is splitting into carbon monoxide and O2, this is called dissociation. This is the association and this is the dissociation. Here the pressure at 2, 3, 4 without considering the dissociation and variable specific heats given as P2, P3, P4. With variable specific heat and dissociation, the pressures at the respective points given as P2 dash, P3 dash, P4 dash. Then relation between the ideal condition pressures and actual condition pressures given, right. For that, it is better to mark the ideal Otto cycle first. The ideal Otto cycle means without considering any change in specific heat and dissociation. The ideal Otto cycle is like this. Ideal Otto cycle consists of isentropic compression, 1 to 2 isentropic compression, followed by 2 to 3 constant volume heat addition, that should be a vertical line, followed by 3 to 4 isentropic expansion, followed by 4 to 1 constant volume heat rejection. That is the ideal Otto cycle. Now, once I consider the effect of variable specific heat and the variable specific heat and dissociation, remember, with increase in temperature for real gas, if temperature increases, the Cp increases, Cv also increases, but the rate of increment in Cv marginally more than that of the Cp, therefore the gamma decreases. Gamma equal to what? Cp by Cv. With increase in temperature, Cp increases, Cv also increases, but rate of increment in Cv marginally more than that of the Cp, therefore gamma decreases with increase in temperature for a real material. Then, as you know, T2 by T1, otherwise in terms of pressures, P2 equal to, pressure after compression P2 equal to P1 into compression ratio power gamma. When this gamma decreases, pressure after compression decreases by considering the effect of variable specific heat and dissociation. Right? Association is developing some heat energy, that is called exothermic reaction. C plus O2 gives rise to CO2, it is developing some heat energy. This is an endothermic reaction. Dissociation is demanding the heat energy, that kind of reaction is called endothermic reaction. That means for splitting the carbon dioxide into carbon monoxide and oxygen, some energy is required. Once we consider the energy demanded by the system for dissociation and variable specific heat, the pressure after actual compression will be less than pressure after ideal compression. Look at the pressure after ideal compression. This is the pressure after ideal compression, I can mark as P2. But because of the dissociation effect and irreversibility effect, for the same volume limits, or for the same compression ratio, the compression is proceeding from 1 to 2 dash like this. This is the compression process representation. 1 minute, let me draw it clearly. The compression process, 1 minute, you should be very careful, the compression process with dissociation may be like this, 1 to 2 dash. Look at the pressure after actual compression by considering the variable specific heat and dissociation. P2 dash, I can conclude that P2 dash less than P2. Then 2 dash to 3 dash, is the pressure rise process while the heat is adding, P3 dash. Pressure after ideal heating, P3. After actual heating, P3 dash. From that I can conclude that P3 dash is less than P3. Then expansion is proceeding from 3 dash to 4 dash. It is 4 dash. Look at the pressure at state 4 dash. Pressure at state 4 dash, I can say pressure at state 4 dash is less than P4. That means once we consider the effect of dissociation and variable specific heats, the cycle is becoming 1, 2 dash, 3 dash, 4 dash, 1. Therefore, pressure at state 2 dash is less than pressure at state 2. Pressure at state 3 dash is less than pressure at state 3. Pressure at state 4 dash is less than state 4 pressure. That means P2 less than P2, P2 dash less than P2, P3 dash less than P3 and P4 dash less than P4, right? Those are the what effects. Look at the options. P2 less than P2 dash not correct. P3 less than P3 dash not correct. P2 more than P2 dash, okay. P3 more than P3 dash, but P4 is less than P4 dash, no. P4 is more than P4 dash, right? Therefore, this is not, this statement not correct, right? These two are correct. P2 is more than P2 dash, P3 more than, okay. Therefore, C also not correct. Look at the D, P2 more than P2 dash and P3 more than P3 dash. Option D is absolutely correct. Understood clearly? Yes. Then look at the another question asking like this. An air standard diesel cycle consists of two reversible adiabatic process, one constant pressure heat addition and one constant volume heat rejection. Two adiabatic, two constant volume, no. These are the process for Otto cycle. Two constant volume, two isothermal, right? No, that is for what? Stirling cycle. One constant pressure, one constant volume and two adiabatic process, absolutely correct. For the diesel cycle, heat addition is at constant pressure, heat rejection at constant volume and compression, expansion taking place adiabatically. Therefore, C is correct. Look at the last one. One constant pressure, one constant volume, two isothermal, no. C is absolutely correct, okay. So, these are the process, two adiabatic, two constant volume for Otto cycle. Two constant volume, two isothermal are for Stirling cycle. Okay, na? I hope you are all clearly following. Okay, I am trying to explain the each and every point at your easily understanding level. Okay, are you following clearly? Yes. Then look at the next one, right? Look at this one. The figure below shows a thermodynamic cycle. Look at the thermodynamic cycle undergone by a certain system. Find the mean effective pressure. You are asked to decide mean effective pressure in kilopascal. As you know, mean effective pressure equal to, let me write the formula first. Mean effective pressure is equal to network divided by swept volume. Network divided by swept volume. Swept volume equal to what? If I say, right, this is the V1 and this is the V2, this is the V2. It can be written as network divided by swept volume is V1 minus V2. V1 minus V2. Let me mark the V1. V1 equal to what? 0.03 and V2 equal to 0.01. Okay. 0.01. So, V1 I got, V2 I got it. Network equal to area within the cycle. Network equal to area within the cycle, that is looking like a right angle triangle. Area of the right angle triangle or area of the triangle half into base into height. Half into base is what? V1 minus V2. Into height is, right, let this is the right, this is the right, this is the P1, this is the P2. Okay. Right, height is, no, simply 500 minus 200, right, 500, this is the 500 minus 200, right, 500 minus 200. Let me mark it. Otherwise, directly let me write the values, half into base into height. Right, look at the base. Base is, right, V1 minus V2, 0.03 minus 0.01 into height is, directly I am writing for avoiding the confusion, 500 minus how much? 200. Simplify it. Half into it is equal to 0.02 into 300. 300 into 0.02, 6 by 2 equal to 3. That is the net work. That net work divided by swept volume is giving the net work divided by swept volume is giving the mean effective pressure. Therefore, mean effective pressure equal to net work by swept volume V1 minus V2. Net work is 3 kilojoules. Swept volume is V1 minus V2, 0.03 minus 0.01. 0.03 minus 0.01. It is equal to 3 divided by 0.02. You simplify this value, right? 3 by 0.02 is giving 150 kilopascal or kilonewton per meter square. That is the mean effective pressure for the given cycle, 150. Options are not available. Answer is 150, which is in kilopascal or kilonewton per meter square. Understood clearly? That is the value my calculator has shown, right? Now, let us take the another question asking like this. Isentropic compression of saturated vapor of all fluid leads to superheated vapor. Is it true or false? Isentropic compression of saturated vapor of fluid lead to superheated vapor. Absolutely correct. Look at the TS diagram. Temperature versus entropy diagram. The saturation dome with the TS coordinate system may be looking like this. The apex point is representing the critical point. During the compression process, as you know, pressure increases. Let the pressure before compression is P1 and the pressure after compression is P2. Since it is given for compression process. That too, what kind of vapor is compressing? Saturated vapor. Then you try to mark the beginning of the compression. Wherever the P1 is meeting the saturated vapor curve, that is the state representing the beginning of the compression. It is compressing isentropically. This is the representation of isentropic compression. That should be a vertical line. That is the representation of isentropic compression. Right? Though it is not looking like vertical, it should be a vertical isentropic compression. By the time the dry saturated vapor refrigerant is isentropically compressing, definitely the dry vapor is becoming superheated vapor. This is the two-phase region. Liquid plus vapor. This is the subcooled region. This is the saturated vapor curve. This is the superheated region. That means by the time the dry saturated vapor is compressing isentropically, definitely it is becoming superheated vapor. That's why it is given true. The statement given is true. Understood clearly? Yes. Then look at the next question. It is a match list 1 with list 2 kind of question. Under list 1, it is given like this: gas turbine, petrol engine, Stirling engine, diesel engine. Diesel engine means diesel cycle. Stirling engine means Stirling cycle. Petrol engine means petrol cycle. Petrol means auto cycle. Gas turbine cycle is the Brayton cycle. Right. Now, look at the cycles. Constant volume heat addition and constant volume heat rejection. Constant volume heat addition, constant volume heat rejection. In the Otto cycle, heat addition at constant volume heat addition and constant volume heat. Let me read all the statements. Constant pressure heat addition and constant volume heat rejection. Constant pressure heat addition, constant volume heat rejection I can mark for diesel engine, diesel cycle. Constant pressure heat addition and constant pressure heat rejection. constant pressure heat addition and constant pressure heat rejection for the Brayton cycle, gas turbine cycle. Heat addition at constant volume followed by heat addition at constant temperature, heat rejection at constant volume followed by heat rejection at constant temperature, that is for Stirling cycle. For both Stirling cycle and Otto cycle, heat addition and heat rejection at constant volume, that is why I did not decide it. Anyhow, petrol engine is Otto cycle. For the Otto cycle, heat addition at constant volume, heat rejection at constant volume. Therefore, A3 comma B1 comma C4 and D2 This is the correct option. That is the correct order. I hope all of you clearly understood. Understood or not? Yes, very simple problem, but given for 2 marks in the year 95. Okay. Similarly, look at the next one. It is asking like this. In order to burn 1 kilogram of methane CH4 completely, the minimum number of kilograms of oxygen needed is, take an atomic weight of hydrogen, carbon and oxygen 1, 12 and 16 respect. Complete combustion, right? The methane is completely combusted. Because of the complete combustion, right, the combustion products are maintaining carbon dioxide, that means no carbon monoxide, and water vapor. The methane CH4 reacting with oxygen to produce carbon dioxide and water vapor, H2O. Now let us have the balance. H4, 4 hydrogen atoms, multiply with 2, C1, okay. Now look at the oxygen, 2O, right. Now it is chemically balanced. Now let us write the molecular weight on both sides. CH4, right, C 12 plus 4, 16. 16 kg of methane requires, right, 2 into 32, 64 kg of oxygen to produce 44 kg of CO2 and 18, right, 18 into 2, 36 kg of, right, H2O. Understood clearly? O, atomic number, atomic weight of O, 16 plus 2, 18 into 2, 36, correct. So 16 kg of methane demanding 64 kg of oxygen to produce 44 kg of carbon dioxide plus 36 kilograms of H2O. But what it is asking, how many kg of oxygen is needed? So 1 kg of methane for its complete burning requires 64 by 16, that is 4 kg of oxygen. That means for complete combustion of 1 kg mass of methane, 4 kg of oxygen is required. 4 kg of oxygen is required. Option B is absolutely correct. Understood clearly? Yes. Then look at the next question, asking like this. Consider a 2-stage reciprocating air compressor, number of stages Z equal to 2, with a perfect intercooling operating at the best intermediate pressures. Okay. Air enters the low pressure cylinder at 1 bar pressure. The suction pressure PS is equal to 1 bar pressure. This suction pressure I can write as P1 with a temperature T1 equal to suction temperature equal to 27 plus 273, 300 Kelvin. Okay. And leaves the high pressure cylinder at 9 bar, that is the delivery pressure. Let me mark the diagram. low pressure cylinder, this is the high pressure cylinder. For the low pressure cylinder, local atmospheric air is entering from state 1 with a pressure P1, that P1 is marked as PS. Because of the compression in the low pressure compressor, pressure increases. This is the state 2 where the pressure is P2. Then the air is cooled in the intercooler. This intercooler is a perfect intercooler working at constant pressure. Because of the cooling at constant pressure, only temperature decreases to T3. The T3 will be equal to T1. That is the condition of ideal intercooling. The temperature after intercooler must be equal to temperature at the beginning of the low pressure compressor, right? So with this pressure P2 and low temperature T1, air is entering to HP compressor where the further compression is happening. Because of the further compression, temperature is increasing from T3 to T4. Pressure is from P2 to P3. This P3 itself is the delivery pressure. That delivery pressure is given as 9 bar. Therefore, P3 equal to delivery pressure is equal to 9 bar. 9 bar. Assume index of compression and expansion in each stage 1.4. Index of compression equal to index of expansion equal to 1.4. That is the adiabatic index. R value given 286.7 joules per kg Kelvin. The work done per kg in the high pressure cylinder. The work done per kg of air in the high pressure cylinder. It is asking only in the high pressure cylinder. Once again, the work done per kg of air in the high pressure cylinder. If I say work for low pressure cylinder is W1, work for high pressure cylinder is W2. That W2 equal how much? That is the question. You know, work required for, let me write it. For the ideal intercooling, remember the condition is work required for low pressure compressor equal to work required for high pressure compressor. Therefore, the work required for low pressure compressor equal to work required for high pressure compressor equal to N by N minus 1 into RT1 into P2 by pressure ratio per stage P2 by P1 power N minus 1 by N minus 1. P2 is the intermediate pressure. That P2 equal to root over P1 P3. P2 equal to P1 P3 root over. From this I can write that P2 square equal to P1 P3 or P2 by P1 is equal to P3 by P2. Pressure ratio per each stage remains same. Anyhow, right here the P2 by P1 I need to decide the P2 value because P3 is given. P2 value, P2 equal to root over 1 into delivery pressure how much? 9. That is equal to 3 bar. Okay, right, that is the 3 bar. Okay, P2 by P1 3 bar. N by, right, N is 1.4 divided by 0.4 into, right, into RT1. R equal to how much given? Right, R, since the answer is asking, okay, no problem. You can take in either joules per kg Kelvin or kilojoules per kg Kelvin. I am taking in kilojoules per kg, 0.2867, 0.2867 into T1. What is the T1 value? T1 value given 300 Kelvin. 300 into P2 by P1, right? P2 by P2 is 3 by 1 power 0.4 by 1.4 minus 1. You simplify this value. Whatever the answer you are getting, whatever the value your calculator is showing, that is the answer. Okay. So, my calculator has shown, right? Please check it, 111.13 kilojoules per kg. That is the value, but formula, this is the required formula for deciding the work required for HP pressures, high pressure cylinder or high pressure compressor, right? Just to you verify it, my calculator has shown this value 111.13 kilojoules per kg. Look at the options. Option A itself is absolutely correct. I hope all of you clearly understood. It is not the total work. It is not asking the total work. The work done per kg of air in the high pressure cylinder only, not the total work. If you want, right, get the total work, or if it is asked to decide the total work, right, this value plus multiply with 2, because the work required for LP compressor equal work required for HP compressor when the intercooler is working ideally. I hope all of you clearly understood it. Right, that point you have to, right, mark it. Shall I move to next one? Yes, look at the next one. It is asking like this: air Cp value given, gamma value given, right? Shall I should I take gamma value? How much? 1 minute. Gamma 1.4. Okay, no problem. Okay, gamma 1.4 enters a compressor at a temperature of 27 degrees centigrade. Initial temperature T1 equal to 27 plus 273 is equal to 300 Kelvin. Compression pressure ratio Rp equal to P2 by P1 is equal to 4. Assuming an efficiency of the, right, compressor, isentropic efficiency of the compressor is given 0.8. The work required in kilojoules per kg. What is the work required for compression? Very simple. For that, better to mark the, right, TS diagram. Compressor efficiency given means indirectly you are asked to consider the effect of friction. In the compression process, as you all know, pressure increases. Let the P1 be the pressure before compression, pressure after compression is P2. Then if the compression is happening isentropically, ideally, this is the representation of isentropic compression, is also called ideal compression. Because of the ideal compression, temperature is increasing from T1 to T2. But compressor efficiency given means indirectly you are asked to consider the effect of friction. Once we consider the effect of friction, the compression curve deviating towards the increase in entropy. Then temperature after actual compression is T2 dash. Then what is the work required for compression? Work required for a compression equal to Cp into T2 dash minus T1. For that we need to decide the T2 dash. To decide the T2 dash value, first let me take the isentropic compression process. For this isentropic compressor, T2 equal to T1 into Rp power gamma minus 1 by gamma. T1 300, Rp value given 4 power 0.4 divided by 1.4. You simplify this value for getting the T2. My calculator has shown the T2 value 445.8. 445.8 Kelvin. That is the temperature after ideal compression. But compression efficiency equal to ideal temperature rise by actual temperature rise, T2 dash minus T1. Okay. Compression efficiency, how much it is given? 0.8. 0.8 is equal to T2, 445.8 minus 300 divided by T2 dash to be found minus 300. From this get the value of T2 dash. Simplify it. My calculator is given 482.25, 482.25 Kelvin, that is the T2 dash. Then compression work equal to Cp, how much Cp given? 1 only, right? 1 into T2 dash, 482.25, 482.25 minus 300. You simplify this value for getting the answer 182.25, 182.25 kilojoules per kg Kelvin, kilojoules per kg only, not Kelvin, kilojoules per kg. That is the work required for this particular compressor. 182.25, 182.25, approximately 182. Understood clearly? I hope all of you clearly understood. Understood or not? Yes, that is all about the air standard cycles. Okay, thank you. Dear students, now let us discuss the solutions for psychrometry. From this unit, no 1 mark question, only 4 2 marks questions are there. Okay, look at the very first 2 marks question, very simple question asked, right, in the year 89, very old question. Wet bulb depression under saturated ambient air condition. You know, saturated ambient air condition means relative humidity equal to 100%. The dry bulb temperature is equal to wet bulb temperature is equal to dew point temperature. He is asking wet bulb depression for saturated air. As you know, wet bulb depression equal to difference between dry bulb temperature and wet bulb temperature. For the saturated air, dry bulb temperature and wet bulb temperature both are equal. Therefore, this difference is becoming 0, means wet bulb depression is 0. Look at the option C. Option C is absolutely correct. Understood clearly? Very simple problem, but given for 2 marks. Okay. Now let us take the another question asking like this. Atmospheric air from 40 degrees centigrade, 60% relative humidity can be brought to 20 degrees centigrade, 60% relative humidity by different process are given. Here initial dry bulb temperature dBT1 equal to 40 degrees centigrade with relative humidity 60%. After the system or air brought to the final state, final dry bulb temperature dBT2 20 degrees centigrade, the RH value equal to same, that is 60%. To bring the atmospheric air from this state to this state, what is the type of process required? For that, let me mark the psychrometric chart. Specific humidity on the ordinate, dry bulb temperature and the abscissa. Let me complete it. This is the psychrometric chart. This line is representing saturation curve. Over that saturation curve, RH equal to 100%. Okay, that means that is the state of the saturated air. Now this is the initial state where the initial temperature is 40 degrees centigrade, RH value 60%. This may be the final state. This may be the final state of the air. The final temperature is given 20 degrees centigrade, but RH remains same. For bringing the air to the state 2 from state 1, I must cool the air, that is called sensible cooling process, and I must remove some moisture present in the air, that is called dehumidification. So 1 to 2 sensible cooling process, 2 to 3 dehumidification process. The combined effect of cooling and dehumidification is marked like this. The 1 to 2 is representing the cooling and dehumidification. Cooling and dehumidification. 1 to 2 dash sensible cooling, 2 dash to 2 dehumidification, 1 to 2 is the cooling and dehumidification. Relative humidity, right, though it is given relative humidity remains same, but for all practical cooling and dehumidification process, it is not compulsory to maintain the relative humidity remains same. That depends on the rate of cooling and rate of dehumidification. Okay. Anyhow, for this particular case, though the relative humidity remains same, the process required is cooling and dehumidification. Look at the option. Option A itself is absolutely correct, cooling and dehumidification process. But dear friends, remember, in the cooling and dehumidification process, a relative humidity may be constant or may be decreasing or increasing. That depends on the rate of cooling and rate of dehumidification. Okay. Having that, right, conclusion, let us move to the next question. Look at this one, asking like this: if moist air is cooled by sensible heat removal process, that means moist air is cooled by sensible heat removal means sensible cooling process, which of the following is true? For that, it is better to mark the psychrometric chart once again. Psychrometric chart. Dry bulb temperature on the abscissa, specific humidity on the ordinate. Sensible cooling process, the method of decreasing the dry bulb temperature of the atmospheric air at constant specific humidity is called sensible cooling process. Sensible cooling process. That is the representation of the process for the given sensible heat removal process. Look at the option A, neither relative humidity nor specific humidity changes. Specific humidity does not change, but relative humidity is going to increase, because if I mark a curve parallel to the saturation curve through the state 2, that is very close to saturation curve. Therefore, right, this is the RH1 curve, RH2 curve. RH2 is very close to saturation curve, therefore RH2 is more than RH1. That means during the sensible cooling process, relative humidity increases, but it is given that relative humidity cannot be changed. Specific humidity changes, no, specific humidity remains constant. Both relative humidity and specific humidity change. Specific humidity is not changing, relative humidity is increasing, right? Therefore, C also not correct. A not correct, B not correct, C not correct, none of the above, right? Absolutely correct. Because of the sensible cooling, that means effects of sensible cooling process, specific humidity remains constant. As long as the specific humidity remains constant, dew point temperature also remaining constant. But dry bulb temperature decreases. Dry bulb temperature decreases. Let me mark the wet bulb temperature line through state 1 like this. These are TW1, TW2. The wet bulb temperature value is increasing from bottom left to top right. Therefore, wet bulb temperature decreases. Since wet bulb temperature line and constant enthalpy lines are identical, when the wet bulb temperature is decreasing, definitely enthalpy decreases. Specific volume decreases. What about the RH value? RH value increases. These are all the effects of sensible cooling process. Anyhow, D is correct. Okay na? Similarly, look at the another one. It is given like this. Select statements from list 2 matching the process in list 1. Entry your answer as D, comma C if the correct choice for 1 is D and that for 2 is C. Okay. That means if the D is matching for 1, you mark the 1D, and C is matching to 2, mark the 2C. Look at the one, cooling and dehumidification process. Chemical dehumidification process. Cooling and dehumidification process. Let me mark the cooling and dehumidification. Let me mark it. The cooling and dehumidification process can be marked like this. Dry bulb temperature and specific humidity. Let me mark the separate sensible cooling. 1 to 2 sensible cooling. 2 to 3 dehumidification. Then 1 to 3 be the combined effect of cooling and dehumidification. So that is the representation of cooling and dehumidification. Now chemical dehumidification process. Chemical dehumidification process are happening along with the constant wet bulb temperature line, right? Better to mark the chemical dehumidification process must be happening to the dry bulb temperature, specific humidity. Chemical dehumidification process is happening along the constant wet bulb temperature line, that is the constant wet bulb temperature line. Chemical dehumidification process may be beginning at state 1. 1 to 2 be the chemical dehumidification process representation. Okay. Then, right, list 1 cooling and dehumidification marked in the that particular first diagram, chemical dehumidification. Then look at the list 2. Dry bulb temperature increases but dew point temperature decreases. Dry bulb temperature increases but dew point temperature decreases. Look at the chemical dehumidification process. In the chemical dehumidification process, look at the dry bulb temperature is increasing from T1 to T2, and dew point temperature, horizontal lines are giving dew point temperature. This is the TDP1, dew point temperature state 1. This is the TDP2, dew point temperature state 2. That means dew point temperature is decreasing, dry bulb temperature increases during the chemical dehumidification process. Therefore 2A correct. 2A correct. Next, dew point temperature increases and dry bulb temperature remains unchanged. No, right? In both cases, dry bulb temperature is not constant. Therefore, B is absolutely wrong. Dry bulb temperature and wet bulb temperature decreases. Dry bulb temperature and wet bulb temperature. Look at the cooling and dehumidification. Dry bulb temperature is decreasing from T1 to T2. Wet bulb temperature is decreasing from TW1 to TW2, TW3, right? This is the T3, TW3. That means in the cooling and dehumidification, dry bulb temperature is decreasing, wet bulb temperature also decreasing. Both dry bulb temperature and wet bulb temperature decreases. Therefore, this is for 1. Cooling and dehumidification 1. 1C. 1C. Okay. Dry bulb temperature decreases, but dew point temperature increases. No, dry bulb temperature decreases, dew point temperature increases. No, no. So anyhow, right? Anyhow, here it is 2A, 1C is absolutely correct. 2A, 1C, right? 2A, 1C, 1 minute. 2A, 1C absolutely correct. That is the answer. I hope all of you clearly understood. right? That is all about the psychrometry. Understood clearly? Yes. Dear students, now let us discuss the detailed solutions for the highly weightage unit before 2000, that is Rankine cycle. Highest weightage was given for Rankine cycle before 2000, but these days 1 mark question can be expected from the Rankine cycle. Let us take the 1 mark questions. Look at the first 1 mark question asked in the year 1994, like this. For a given set of operating pressure limits of a Rankine cycle, the highest efficiency occurs. That means for the same operating pressure limits among the given cycles, which can maintain the highest efficiency: saturated cycle, superheated cycle, reheat cycle, regenerative cycle. Undoubtedly, regenerative cycle can maintain the highest efficiency for the given pressure limits. The concept of regeneration was given by Stirling, but practically Stirling cycle is not possible. Once again, the concept of regeneration was given by Stirling, but practically the Stirling cycle is not possible. But we are getting the benefit of regeneration with gas turbine power plant and steam turbine power plant. Dear friends, believe me, wherever the concept of regeneration is used, whether it is for gas turbine power plant or steam turbine power plant, definitely thermal efficiency increases. Okay. So anyhow, Rankine cycle is the theoretical cycle for the practical steam turbine power plant, whereas Brayton cycle is the theoretical cycle for the constant pressure gas turbine power plant. Option D is absolutely correct. Okay. Similarly, look at the next question. It is asking like this. For a single stage impulse turbine with rotor diameter 2 meters, rotor diameter D given 2 meters and a running speed RPM given 3000 revolutions per minute. When the nozzle angle is 20 degrees, nozzle angle can be marked as alpha 20 degrees. The optimum velocity of the steam is, you are asked to decide what is the optimum velocity of the steam. V1 is how much? Okay. For that, you know, optimum blade speed ratio for the single stage impulse turbine, that is D level turbine, is U by V1 is equal to cos alpha. U by V1 equal to cos alpha by 2, because it is a single wheel turbine, cos alpha by 2. From this you can decide the V1. V1 equal to 2U by cos alpha. 2U by cos alpha. U equal to blade speed, U equal to pi dn by 60. Pi dn by 60. It is equal to pi into d value given 2 meters, n value given 3000, dividing by 60. That is the U value. Then V1 equal to 2 into, look at the U value, pi into, right, 2 into 3000 divided by 60 into cos alpha. Look at the alpha value, alpha equal to 20 degrees. You simplify this value for getting the optimum steam velocity. My calculator has shown 668.64 meter per second. That is the value my calculator has shown, 668. Look at the option C. Option C is absolutely correct. Understood clearly? Yes. Dear friends, remember, single stage impulse turbine means D level turbine. D level turbine. For a D level turbine, optimum blade speed ratio rho optimum equal to cos alpha by 2. Okay. Now let us take the another important question. It is asking like this in the year 1995. In adiabatic flow with friction, the stagnation temperature along the streamline increases or remaining constant. Stagnation temperature. Let us mark the temperature versus entropy diagram. For the static pressure limits P1 and P2, these are the static pressure limits. For these static pressure limits, the isentropic process can be marked like this: 1 to 2, 1 to 2. That is the isentropic process representation. But once we consider the effect of stagnation, this is the P01 stagnation pressure at state 1. This is the stagnation pressure at state 2, P02. Then look at the quantity. This I can mark as 0, 1 stagnation state, generally marked with 0, or stagnation properties generally marked with naught. These are 0, naught. This is equal to, this quantity is equal to V1 square by, V1 is the velocity, V1 square by 2 Cp. By the time this much amount of velocity is decreasing, stagnation temperature is increasing from T1 to T01 at state 1. If the process is isentropic, the process will be continued up to naught 2. This is the naught 2. This is the T2. This is the stagnation temperature after compression if the process is isentropic. But with friction, once we consider the effect of friction, the curve is deviating towards the increase in entropy. This is the naught 2 dash. This vertical line is representing V2 square by 2 Cp. Otherwise, let me write it clearly. Your understanding is very, very important. This quantity is equal to V2 square by 2 Cp. By the time the velocity at exit is decreasing to a value V2, temperature is increasing from this to this one. Now look at the stagnation temperature with friction, T02 dash. Without friction, stagnation temperature T02. With friction, stagnation temperature T02 dash. T02 dash, from the diagram, it is concluded that T02 dash more than T02. That means stagnation temperature increases if you consider the effect of friction. Okay. Then look at the options. In adiabatic flow with friction, the stagnation temperature along the streamline increases. With friction, the stagnation temperature increases. Understood clearly? Yes. Then next question, look at this one, asking like this: consider a Rankine cycle with superheat. If the maximum pressure in the cycle is increased without changing the maximum temperature and the minimum pressure, the dryness fraction of the steam after isentropic expansion will increase or decrease. Here only the maximum pressure in the cycle is increased without changing the maximum temperature and minimum pressure. For that, let me mark the TS diagram. Temperature versus entropy diagram. The saturation dome can be marked like this. That is the saturation dome. Let me mark the two pressure limits. Minimum pressure is the condensation pressure, this is the condenser pressure, and maximum pressure is the boiler pressure. Boiler pressure. What it is given? Consider the Rankine cycle with superheated. If the maximum pressure in the cycle is increased, right, for the same maximum temperature. For that, let me mark the maximum temperature. This is the T max. Wherever that maximum temperature and maximum pressure are meeting, that is the initial state. Then expansion, isentropic expansion can be marked like this, 1 to 2. If the maximum pressure is increasing from PB to PB dash, the maximum pressure is increasing from PB to boiler pressure PB to PB dash. This is the PB dash. Here PB dash more than PB. For the same maximum temperature, look at the new state. This is the 1 dash. Wherever the new maximum pressure and new maximum temperature are meeting, that is the state 1 dash. For the same minimum pressure, that is the condensation pressure, this is the isentropic expansion from 1 dash to 2 dash. Okay. Now, because of that increase in boiler pressure, what he is asking? The dryness fraction of the steam after expansion. Look at the dryness fraction at state 2, x2, that is very closer to saturation curve. x2 dash with high boiler pressure. Here x2 dash is less than x2. That means dryness fraction decreases when you increase the maximum pressure for the same maximum temperature and minimum pressure. Anyhow, dryness fraction decreases. Dryness fraction decreases means the moisture content increases. Anyhow, the dryness fraction of the steam after isentropic expansion will decrease. Dryness fraction will be decreasing. Once again, consider the Rankine cycle with superheat. If the maximum pressure in the cycle is increased without change in maximum temperature and maximum minimum pressure, the dryness fraction of the steam after isentropic expansion definitely decrease. Right? Decrease, correct. Absolutely correct. Okay. So, understood clearly? Yes. Then look at the next question. Which among the following is the boiler mounting? Blow-off cock, this is the boiler mounting. Feed pump, boiler accessory. Economizer, boiler accessory. Superheater, also boiler accessory. Among the given equipment, blow-off cock is coming under the boiler mounting. Option A, absolutely correct. Okay. Now look at the another question. If Vn and alpha are the nozzle exit velocity and the nozzle angle in an impulse turbine, the optimum blade speed, optimum blade velocity, very simple. For simple impulse turbine, the optimum blade speed ratio equal to U by V1 is equal to cos alpha by 2. From this U equal to optimum blade speed U equal to V1 cos alpha dividing by 2. This V1 it is given as Vn. That V1 is given as Vn. Therefore, optimum blade speed U equal to Vn cos alpha dividing by 2. Vn cos alpha dividing by 2. Vn cos alpha dividing by 2. Look at the option C. Option C is absolutely correct. Are you following clearly? Yes. Then next question. Look at this one. A Curtis stage, Ratu stage and 50% reaction stage in a steam turbine are examples of. Curtis stage is the velocity compounding. Velocity compounding. Ratu stage is the pressure compounding. And 50% reaction stage is the reaction turbine or Parsons reaction turbine. Parsons turbine. Different types of impulse turbine? No, this is the reaction turbine. Different types of reaction turbine? Not correct. A simple impulse? No. Velocity compounding? Yes. Impulse stays, pressure compounding stays, and reaction stays. Absolutely correct. Velocity compounding impulse turbine is called Curtis turbine. Pressure compounding impulse turbine is called Rato turbine. 50% reaction turbine is called Parsons reaction turbine. Understood? Option D. Option D is absolutely correct. Okay. Similarly, look at the next question. It is asked in the year 2000. Very simple question. Which of the following is a pressure compounded turbine? Pressure compounded turbine is Rato turbine. Curtis turbine is the velocity compounded turbine. Rato turbine is the pressure compounding turbine. Option C is absolutely correct. Okay, na? Next, 2 marks questions. Look at the first one. An economizer in a steam generator performs the function of, economizer is one of the boiler accessory used for the steam boilers for preheating the feed water before it is entering to the boiler drum. Anyhow, economizer function is for preheating the feed water. Preheating the combustion products? No. Preheating the feed water, absolutely correct. Economizer for preheating the feed water, whereas air preheater is for preheating the air which is supplied to the combustion chamber for the purpose of firing the fuel. Anyhow, option B, absolutely correct. Okay. Similarly, look at the next question asked in the year 89. The fundamental objective of employing the condenser in a steam power plant is reduce or increase the dash of the steam, means quality of the steam or dryness fraction of the steam. The fundamental objective of employing the using the condenser in steam turbine power plant for reducing the quality of the steam. It is like this. Look at the TS diagram, temperature versus entropy diagram. Dear friends, remember, by using the concept of condenser, you can expand the steam in the steam turbine below atmospheric pressure, because in the condenser, by using the air extraction pump, we are practically maintaining the pressure well below the atmospheric pressure. If there is no condensation process, the Rankine cycle is looking like this. This is the boiler pressure. Then without condenser, if you want to leave the steam to atmosphere, this is atmospheric pressure. Okay. Then for these pressure limits, look at the expansion. Expansion can be happening from 1 to 2. Isentropic expansion, right, without condenser, 1 to 2. Without condenser. But with condenser, you can maintain the low pressure in the condenser. Therefore, the pressure of the steam can be dropped during the expansion process in the turbine to PC, that is called condensation pressure. Then for the same initial state, the steam can be expanding up to 2 dash. So by the time the steam is expanding to drop the pressure from boiler to the pressure below the atmospheric pressure, definitely work output increases. But what about the quality of the steam? Look at the quality at state 2, X2. Look at the state 2 dash, quality is X2 dash. The 2 dash is away from the saturation curve, 2 is very close to the saturation curve, right? Therefore, the X2 dash will be less than X2, because 2 dash is away from the saturation curve. When the state is away from the saturation curve, that is the representation of high moisture or low dryness of the steam, or dryness quantity of the steam, or dryness fraction. Anyhow, the fundamental object of employing the condenser in a steam power plant is to reduce the quality of the steam or dryness fraction of the steam, right. The main intention is for getting the more work by expanding the steam below atmospheric pressure. For that, we are using the concept of condensation for thermal power plant. In case of gas turbine power plant, it is not practically possible to drop the pressure below the surrounding pressure, but in case of steam turbine power plant, right, you can practically maintain very low pressure at the exit of the turbine for the purpose of increasing the expansion work or positive work from the thermal power plant. Anyhow, answer is the fundamental object of employing the condenser in steam turbine power plant is to reduce the quality of the steam or dryness fraction of the steam. Understood clearly? Yes. Then look at the another question asked in the year 90. It is like this. In the Rankine cycle, when superheated steam is used, means let us mark the TS diagram once again for Rankine cycle, temperature versus entropy, right. Right. Otherwise, you can also mark the HS diagram directly. HS diagram, enthalpy versus entropy diagram, enthalpy versus entropy diagram. Let me mark the saturated vapor curve. This is the critical point. This is the saturated vapor curve. For the pressure limits of P1, pressure of the steam before expansion P1, pressure of the steam after expansion P2. Now, if I use the dry steam for expansion of the steam, if I use the dry steam for the expansion over the turbine blades, this is the state 1, 1 to 2 is the isentropic expansion. Look at the enthalpy drop is from H1 to H2. Ideally, that enthalpy drop is equal to turbine work. Therefore, turbine work equal to H1 minus H2. Let me write it clearly, right. For saturated vapor, at the inlet, the work given by the turbine equal to H1 minus H2. But if I go for the superheated steam for the same pressure limits, this is the T1, wherever the P1 and T1 are meeting, that is the state 1 dash. Expansion is proceeding from 1 dash to 2 dash. Now look at the new enthalpy limits, H1 dash, and this is the H2 dash. With superheated steam or for superheated steam, at inlet, at inlet, look at the turbine work. New turbine work is H1 dash minus H2 dash. Dear friends, remember this H1 dash minus H2 dash is more than H1 minus H2. Therefore, indirectly, with superheated steam, at inlet of the turbine work increases. Turbine work increases means indirectly net work output of the power plant increases, because net work is what? Net work equal to turbine work minus pump work, right? The superheated steam is obtained by adding the more heat in the boiler. Therefore, pump work remains same. Because of the increase in turbine work, net work output increases. Then what about the specific steam consumption? Specific steam consumption is also called steam rate, equal to 3600 divided by net work output. Because of the increase in net work output, the specific steam consumption decreases or steam rate decreases. Okay. Now what about the heat supply to boiler? Definitely we need to add the more heat for getting the superheated steam. We need to add the more heat to the boiler for getting the superheated steam. Indirectly the heat input to the boiler increases. Then what about the thermal efficiency? Thermal efficiency equal to ratio between the net work output and heat supply to the boiler. Here the network output increases, heat input also increases, then thermal efficiency, right, depending on the rate of increase in network output and rate of increase in heat input. If the rate of increase in network output is more than rate of increase in heat input to the boiler, thermal efficiency increases. Or if the rate of increase in heat input is more than rate of increase in network output, thermal efficiency decreases. For that, experimental results are required. Experimental results are showing that thermal efficiency increases with superheated steam, right. So these are all the effects of using the superheated steam over the dry saturated steam. Anyhow, by using the superheated steam, thermal efficiency can be increased, correct. Steam consumption decreases, that is the specific steam consumption decreases. Next, the steam dryness after expansion increases, yes, because of using the superheated steam. Look at the state 2 dash. State 2 dash is very close to saturation curve, where the dryness fraction is x2 dash, which is more than the dryness fraction at state 2. State 2 is lying away from the saturation curve, therefore moisture content is more. Here the moisture content is less, that means dryness fraction increases. So dryness fraction of the steam increases after expansion. Steam dryness after expansion increases. All of the above absolutely correct, right. It is very important problem. Understood clearly? Option D absolutely correct. Okay na? Yes. Then look at the next question asking like this. When initially dry and saturated steam flows through the nozzle, the ratio of actual discharge to calculated discharge. When the dry steam or superheated steam is entering to the nozzle, steam nozzle, because of the delay in the condensation, dry steam or superheated steam will be expanding in the wet region with superheated steam characteristics. That kind of flow is called supersaturated flow or metastable flow. That metastable flow is happening because of the delay in the condensation. Because of the metastable flow, remember, the actual discharge nearly 4 to 5% more than the ideal discharge. Therefore, when you allow the dry saturated steam or superheated steam to the nozzle, because of the delay in the condensation, actual discharge is more than ideal discharge. Then what is the coefficient of discharge? Right, of course, the ratio of actual discharge to calculated discharge. Since actual discharge is more than ideal discharge, the actual discharge divided by ideal discharge this quantity you are calling as coefficient of discharge is more than 1. So from that the moral is the ratio is greater than 1. Option B is absolutely correct. I hope all of you clearly understood or not? Yes. Then look at the next question. In a Rankine cycle, heat is added. For the Rankine cycle, heat addition at constant pressure and heat rejection at constant pressure. Dear friends, remember, both Rankine cycle and Brayton cycle are having same number of process and same types of process. 2 are isobaric process and 2 are isentropic process. But only the difference is, for the Rankine cycle, vapor is the working fluid, whereas gas is the working fluid for the Brayton cycle. Brayton cycle is the theoretical cycle for gas turbine power plant, whereas Rankine cycle is the theoretical cycle for the practical thermoelectric power plant is also called steam turbine power plant. Anyhow, in a Rankine cycle, heat is added reversibly at constant pressure. Reversible at constant pressure. Of course, major part of the heat addition at constant temperature during the phase change process, by the time the saturated liquid is becoming saturated vapor, temperature remains constant. It is like this. It is like this. Look at the complete TS diagram for the Rankine cycle. This is the saturation dome. Let me mark the two pressure limits. Condensation pressure is the minimum pressure. Boiler pressure is the highest pressure. This is the boiler pressure. Generally, we are allowing the superheated steam to the turbine. You know, this is the superheated state. 1 to 2 is the isentropic expansion in the turbine. 2 to 3 condensation at constant pressure and constant temperature. In the Rankine cycle, the total heat can be rejected at constant temperature. That is the beauty of the Rankine cycle. That means during the entire heat rejection process, according to our diagram, both pressure and temperature remains constant. That means wet steam is becoming saturated liquid. That saturated liquid, while it is pumping, the saturated liquid is becoming subcooled liquid. 3 to 4 isentropic pumping process. Look at the state of the water or state of the liquid while it is entering into boiler, subcooled state. By the time this subcooled liquid is taking the heat from the boiler, the subcooled liquid is becoming saturated liquid. During this process, pressure constant but temperature increases. But once the subcooled liquid is becoming saturated liquid, during the entire phase change process, both pressure and temperature constant. In this part of the heat addition, not only pressure constant but temperature also constant. But entire heat addition is not at constant temperature, because this is also heat addition region where the temperature increases but pressure remains constant. But in this part of the heat supplied, both pressure and temperature remains constant. Once all saturated liquid particles are becoming saturated vapor particles, because of the further heat addition, again the temperature increases but pressure remains constant. That means 4 to 1 is the heat supplied process, right, for the Rankine cycle. In the entire 4 to 1 process, pressure constant but temperature is not constant. Temperature can be constant only a part of the heat addition process. Okay, but in the entire heat addition process, pressure is remaining constant. That's why we selected the heat addition for the Rankine cycle reversible at constant pressure. Understood clearly? Yes. Similarly, look at the next problem. Velocity compounded steam turbine known as Curtis turbine. Simple. Velocity compounded steam turbine, Curtis turbine, uses the principle of converting entire pressure or velocity energy before entering the first stage. So, in the Curtis turbine, the pressure of the steam or pressure energy of the steam is decreasing while it is passing through the nozzle, and this decrease in pressure energy is converted to velocity energy or kinetic energy before it is entering to first stage of the turbine. That means in the velocity compounded steam turbine, that is Curtis turbine, by the time the steam is passing through the nozzle before entering to the first stage of the Curtis turbine, the full pressure is dropping from boiler to condenser in the nozzle only. That drop of pressure is an indication of drop of enthalpy. That drop of enthalpy is converted to kinetic energy before the steam is entering to the first stage of the multi-stage Curtis turbine. That is the answer. Understood clearly? Yes. Then look at the next one. Subsonic and supersonic diffuser having the following geometry. Subsonic and supersonic diffuser, right? You know the relation between the area of the flow and pressure of the flow is, for a, let me write it clearly, for a flow maintains, listen carefully. for a flow maintains heat transfer Q equal to 0, work transfer W equal to 0, the change in pressure dP by dC always negative. Change in pressure by change in velocity always negative for the flow maintaining 0 heat transfer and 0 work transfer. That means if, its meaning is if dP is positive, dC is negative and vice versa. That is the meaning of dP by dC always negative for the flow maintaining 0 heat transfer and 0 work transfer. Okay. And one more important relation is the change in area dA equal to some positive constant K into dP into 1 minus square of the Mach number. That is the relation between the area of the flow and pressure change of the flow. That is the relation between change in area of the flow and change in pressure of the flow, right. K is a positive constant, K is positive quantity, okay. Now it is given, right, diffuser, subsonic diffuser and supersonic diffuser. Let us take the, right, let us take the diverging duct. This is a diverging duct. Na? Assume that a diverging duct is perfectly insulated. This diverging duct is perfectly insulated. Heat transfer Q equal to 0 and no mechanical part is moving within this duct, work equal to 0. Then for this diverging duct, assume the flow is entering with a velocity less than sound velocity A. If the velocity less than sound velocity, then what is the Mach number? Mach number equal to flow velocity by sound velocity. Since flow velocity less than sound velocity, I can say that the Mach number is less than 1. Mach number is less than 1. If Mach number is less than 1, 1 minus square of the Mach number, right, is positive. 1 minus m square is positive. What about the change in area? Change in area dA. dA means final area minus initial area. dA also positive. dA positive. Now you have the relation, right? dA equal to K into dA equal to K into dP into 1 minus square of the Mach number. Here for this diverging duct, right, when the subsonic flow is entering, 1 minus m square quantity is positive, dA positive, K positive. If dA positive, K positive, 1 minus m square positive, dP positive. This, right, fellow is maintaining 0 heat transfer, 0 work transfer. For the flow maintaining 0 heat transfer, 0 work transfer, change in pressure and change in velocity are opposite. That means when the dP is positive, definitely dC is negative. That means this fellow is for increasing the pressure by dropping the velocity. The duct for increasing the pressure by dropping the velocity is called diffuser. What kind of diffuser this one? What kind of diffuser? Right? The subsonic diffuser. That means the diverging duct for subsonic flow, diverging duct is acting as a diffuser. For subsonic flow, diverging duct is acting as a diffuser, right. Now let us take the converging duct. The converging duct is one in which the area of the flow decreases like this. For this converging duct, listen carefully. For this converging duct, let us say the flow is available with a velocity more than sound velocity. Then what about the Mach number? Mach number equal to flow velocity by sound velocity, which is more than 1 because flow velocity more than sound velocity. Assume that duct is also perfectly insulated. Once it is perfectly insulated, heat transfer Q equal to 0 and no mechanical part is moving within the duct, therefore W equal to 0. Then for this kind of system, look at the 1 minus m square. 1 minus m square. Since m is more than 1, 1 minus m square is negative. 1 minus m square is negative. What about the dA? dA means final area minus initial area. dA also negative. When dA is negative, 1 minus m square negative, K positive, dP is positive. When the dP is positive, for the flow maintaining 0 heat transfer, 0 work transfer, dC should be negative. If dP positive, dC negative means this fellow is for dropping the velocity for increasing the pressure. This fellow is for increasing the pressure by dropping the velocity. The duct for increasing the pressure by dropping the velocity is called diffuser. What kind of diffuser is one? Subsonic diffuser. That means the converging duct for supersonic, not subsonic. The converging duct for supersonic flow is acting as diffuser. Anyhow, the subsonic flow or diverging duct for subsonic flow is acting as diffuser. Converging duct for supersonic flow also acting as diffuser. Therefore, the subsonic and supersonic diffuser have the following geometry, that is the divergent and convergent respectively. Option A itself is absolutely correct. I hope all of you are clearly following. I am trying to explain the each and every point at your easily understanding level. Okay? Yes. Now let us take the another question. Look at this one. Boiler rating is usually defined in terms of maximum temperature of the steam in Kelvin, heat transfer rate in kilojoules per hour, heat transfer area in meter square, steam output in kg per hour. Generally, boiler rating is measured in terms of amount of steam generated, which is in tons or kgs in 1 hour. Therefore, option D is absolutely correct. Very simple question, right? Similarly, look at the next one. In steam and other vapor cycles, the process of removing non-condensable gases is called deaeration. Deaeration is the process of removing the dissolved gases, if any, present in the feed water before the feed water is supplied to the boiler. Anyhow, deaeration is the mechanism for removing the dissolved gases, if any, present in the feed water before the feed water is supplied to the boiler. Anyhow, option B is absolutely correct. Okay. Similarly, look at the next one. A steam turbine operating with less moisture is less efficient. Less moisture means dryness fraction is more. Dryness fraction more means it is like this. Let us take the right HS diagram. For the pressure limits, that is the saturated vapor curve. This is the boiler pressure. This is the atmospheric pressure or condenser pressure. This is the another low condenser pressure PC dash. Now, for the superheated steam, somewhere here, if the expansion is happening like this, for the same boiler pressure corresponding to condensation pressure, let this is the condensation 0.1 bar, this is the 0.01 bar. When you maintain the low pressure, right, this is the 2 dash. Look at the dryness fraction x2, right, this is the dryness fraction at state 2 x2, that is closer to saturation curve, right. Let me mark it clearly. Like this. Similarly, this is the dryness fraction at curve at state 2 dash x2 dash. This curve is very far away from the saturation curve. Therefore, I can say that x2 dash is less than x2. When you maintain the less dryness fraction, means more moisture content. Look at the turbine work. Right, for the first case H1 minus H2. But when the condenser pressure is decreasing, new turbine work is H1 minus H2 dash. This H1 minus H2 dash is more than H1 minus H2. Therefore, turbine work, right, is increasing. So that means turbine work can be increased by maintaining the low condensation pressure. But by the time you are maintaining the low condensation pressure, the dryness fraction decreases, right? Dryness fraction decreases. But the thing is, when you maintain the low condensation pressure, because of the increase in turbine work, definitely efficiency is going to increase. A steam turbine operating with less moisture, here at state 2 moisture is less, right? When the less moisture is there, the turbine efficiency is less efficient. When the steam is having the less moisture in the lateral stage of the turbine or at the exit of the turbine work is less, efficiency less. But when the moisture content increases, right, when the steam operating with more moisture, by the time that steam turbine is operating with more moisture, turbine work increases. Because of the increase in turbine work, efficiency is going to increase. Anyhow, a steam turbine operating with less moisture, here moisture is less, right, the turbine efficiency less, but more, right, less prone to blade damage. Because of the less moisture in the steam, the chance of erosion and corrosion is less. That's why the life of the blade is going to increase. That is the meaning of that particular point. Anyhow, a steam turbine operating with less moisture is less efficient and less prone to blade damage because of the less moisture content. If we operate at very low condensation pressure, the moisture content in the lateral stage of the turbine will be very high. That high moisture is causing for damaging the turbine blades, right? For having the better life in the turbine, the moisture content at the exit of the turbine under any circumstances should not be more than 10%. That means at least you have to maintain the dryness fraction even at the exit of the turbine more than or equal to 0.9. The minimum dryness fraction what we need to maintain at exit, the minimum dryness fraction what we need to maintain for increasing the life of the turbine blade should be more than or equal to 0.9. The dryness fraction is less than 0.9, the life of the turbine blade less. That is the meaning of that particular point. Anyhow, a steam turbine operating with less moisture is less efficient and less prone to bleeding. That is the option, less and less, correct. Okay. Similarly, look at the next one. The equivalent evaporation in kg per hour of a boiler producing 2000 kg of steam per hour with enthalpy of content 2426 and feed water enthalpy at 40 degrees centigrade. That means feed water is entering at 40 degrees centigrade. At that 40 degrees centigrade, this is the sensible heat of the water, Then the latent heat corresponding to 100 degrees centigrade given. What you are asked to find? The equivalent evaporation. The equivalent evaporation equal to mass of the steam which is produced into enthalpy of the steam minus enthalpy of the feed water corresponding to 40 degrees centigrade, enthalpy of the feed water at 40 degrees centigrade dividing by H of G at 100 degrees centigrade. That is the formula. Mass of the steam 2000 into H, right, the total enthalpy of the content 2426 minus feed water enthalpy at 40 degrees centigrade 168 dividing by H of G at 100 degrees centigrade 2258. You simplify this calculator for getting the answer 2000 kg per hour, because this quantity will be equal to 2258. Okay. Anyhow, answer is 2000 kg per hour, not second, because it is given per hour na, it is given per hour, kg per hour, not second, printing mistake, kg per hour. Look at the option A. Option A itself is absolutely correct. Are you following clearly? Yes. Then look at the next question, asking like this. A steam power plant has the boiler efficiency 92%. Let me write it. Boiler efficiency 0.92. Turbine efficiency, that is mechanical efficiency, turbine efficiency 0.94. Generator efficiency 0.95. Cycle efficiency 44. Cycle efficiency 0.44. If 6% of the generated power is used to run the auxiliaries, auxiliary components efficiency equal to generated power minus the power consumed by the auxiliaries dividing by generated power into 100. So, here it is given Pg, generated power Pg, given that Pg minus, Pg minus the power consumed by the auxiliary 6% of the generated power, 0.06 of the generated power divided by generated power. It is equal to 1 minus 0.06, 1 minus 0.06 into 100 to get in percentage, that is equal to 94%. Otherwise, you can also write simply 0.94, 0.9, that is the auxiliary components efficiency. Then what you are asked to decide, what is the overall plant efficiency? Very simple. Overall plant efficiency equal to, overall plant efficiency is equal to boiler efficiency multiplied by turbine efficiency, boiler efficiency multiplied by turbine efficiency multiplied by electrical generator efficiency multiplied by cycle efficiency, product of all efficiencies multiplied by auxiliary components efficiency, auxiliary components efficiency, right. So, here it is 0.92 into 0.94, 0.95, 0.94 into 0.95 into 0.44 into auxiliary components efficiency 0.94. You simplify it for getting around 0.34, that is equal to 34%. Let me check it. Let me check it. How much I got, right? Yes, absolutely correct, 34%. So, the overall efficiency of the plant is 34%. Okay, na? Simple problem. Similarly, look at the next question. The following data pertains to a single stage impulse steam turbine. Single stage impulse steam turbine is D level turbine. D level turbine. Nozzle angle given alpha. Nozzle angle alpha equal to 20 degrees. Blade velocity, we are going to mark the blade velocity with u. Blade speed u equal to 200 meter per second. Relative steam velocity at entrance, that is VR1, relative velocity at inlet, VR1, 350 meter per second. Blade inlet angle, blade inlet angle can be marked as theta, 30 degrees. Blade exit angle marked as phi, 25 degrees. If blade friction is negligible, blade friction negligible means VR2 equal to VR1. That is the condition for no friction in the blades. What is the work done per kg? what is the work required per kg of the steam? That is the question. Different options are given. For that, let me mark the velocity triangles. That line is representing the direction of rotation. With respect to direction of rotation, try to mark a point A. From that point, you project a line which is representing the steam velocity V1, making an angle alpha. Since this V1 is making an angle alpha, with respect to direction of rotation, it is developing two component of velocities, right? This is the vertical component of velocity Vf1, and AB is representing the horizontal component of velocity Vw1. Vw1 equal to horizontal component of velocity. That horizontal component of velocity is nothing but V1 cos alpha. Vertical component of velocity Vf1 is nothing but V1 sin alpha. And ABC, let AD be the blade speed. This is the blade speed U. Okay. The vector difference between the V1 and U is the relative velocity. This is the relative velocity at inlet, making an angle theta, that is blade inlet angle. Okay. Now, I am going to mark the outlet velocity triangle. This is the relative velocity at outlet, VR2 equal to VR1 only because no friction. This is the blade exit angle phi, and this is representing the velocity of the steam just after it is coming out from the blade, making an angle beta. Since V2 is making an angle beta, developing two component of velocities, this is the vertical component of velocity, I can say Vf2, A, B, C, D, let this is the E, F. EF is representing the vertical component of velocity and AE representing the horizontal component of velocity Vw2. Then here work done per kg of the steam equal to simply Vw1 plus Vw2 into U. That is the formula. Here U value given, but Vw1 and Vw2 to be found. Okay, for that let us take the triangle. Now Vw1, look at the Vw1. Vw1 equal to, listen carefully, it is quite lengthy problem. Vw1, look at the diagram. Vw1 equal to, otherwise 1 minute. For the triangle, for the right angle triangle, ABC, that is the right angle triangle, you can apply any trigonometric functions. Cos alpha equal to adjacent side, that is Vw1 by hypotenuse V1. V1 is not known, but the thing is this Vw1, look at the diagram, Vw1 equal to AB, that AB I can mark as AD plus DB, Look at the another right angle triangle DBC. For this triangle cos theta equal to dB by VR1, because VR1 known, theta is known. dB equal to VR1 cos theta. So anyhow, Vw1 equal to AD is nothing but U only, U plus dB equal to VR1 cos theta. Look at the U value. How much? 200 plus VR1. VR1 is 350 into cos, look at the theta value. Look at the theta, blade inlet angle theta 30 degrees. 30 degrees. So, it is equal to 200, right. You simplify this value, operate your calculator for getting the VW1. Directly I will write the value decided with my calculator 503.1, it is giving VW1. You simplify this value, VW1, my calculator has shown 503.1, 503.1 meter per second. Then VW2 to be found. VW2 can be found like this. For that, let us take the right angle triangle DEF. For the right angle triangle DEF. For that right angle triangle, right, cos phi equal to U plus VW2, cos phi equal to U plus VW2 divided by VR2, because I know VR2 value, right. Since there is no friction, VR2 equal to VR1, right. Anyhow, from this, no, U plus VW2 is equal to VR2 cos phi. From this, I want VW2. The VW2 equal to U, right, VW2 equal to VR2, quite lengthy problem, easy only, VR2 cos phi minus U. Look at the VR2 equal to VR1, VR2 equal to VR1 equal to 350, cos, what is the phi value given? Cos phi 25 degrees. Minus U, look at the U value 200. You simplify this value, operate your calculator for getting the VW2. My calculator has shown 128.89, 128.89, it is in meter per second. Then work done per kg, of the steam equal to formula VW1 plus VW2 into bleed speed U. Look at the VW1, 503.1, 503.1 plus VW2 128.89, 128.89 multiplied by the bleed speed. What is the bleed speed? Bleed speed 200. Operate your calculator. For getting in kilojoules per kg, dividing with 1000, right, dividing with 1000. Otherwise, from that value, from that term, the answer is, my calculator has shown 126.39 into 10 power 3 joules per kilogram. It is equal to 126.39 into 10 power 3 dividing by 1000 to get in kilojoules per kilogram. These two quantities are cancelled. Finally, it is 126.39 unit is kilojoules per kilogram. That is the answer, 126.39. Look at the options, 126.39, 126 approximate value, nearest value, option A, 124. Understood clearly? Easy problem only, but quite lengthy problem. Understood or not? It is asked in the year 97. Okay? Shall I move to next one? Yes. Look at the next one. It is asking like this. Consider an actual regenerative cycle with one open feed water heater for each kg of steam entering the turbine. For each kg of the steam entering the turbine. Better to mark the diagram like this. This is the steam turbine. For this steam turbine, the amount of steam entering is 1 kg. Okay. If m kg steam with a specific enthalpy H1 is bled from the turbine. Bled from the turbine means before the steam is completely expanding, a part of the steam is extracted. Right? Among the 1 kg, m kg mass of steam is extracted with enthalpy H1. With enthalpy H1. Okay. Then the remaining steam which is expanding from this is, let us do the state 1, state 2, state 2 to state 3, the amount of steam expanding is 1 minus m. That 1 minus m kg mass of steam is expanding from 2 to 3 and that steam is condensed in the condenser. Then 1 minus m kg mass of condensate is available from the condenser. Okay. Let me complete. If m kg steam with a specific enthalpy H1 is bled from the turbine and the specific enthalpy of the liquid water entering the heater is H2. Now let us take the feed water heater. Feed water heater. Let me. Feed water heater. This is the feed water heater. Open feed water heater where the bled steam and 1 minus m kg mass of saturated liquid both are mixing. Here 1 minus m kg mass of liquid, it is clearly given, and specific enthalpy of liquid water entering the heater is H2. This 1 minus m kg mass of liquid is mixed with the m kg mass of bled steam maintaining the enthalpy H1. Then H3 be the specific enthalpy of the saturated liquid leaving the heater is. While it is leaving, the enthalpy of the saturated liquid is H3. Here quantity, right? So 1 minus m plus m, 1 minus m plus m is equal to 1 kg. Finally 1 kg mass of liquid is available. Okay. Then what is asking? Then H3 is the specific enthalpy of the saturated liquid having the heater equal to what is the H3 in terms of H1 and H2. Further let us write the energy balance equation. Energy balance equation says that sum of the energies entering to system must be equal to energy leaving from the system. Energy leaving from the system is 1 kg mass of material into H3. It must be equal to m into H1 plus 1 minus m into H2. So H3 equal to m H1 plus H2 minus m H2. That is the H3. Here H, right? Here it can be written as, let me take another slide. H3 equal to m H1 plus H2 minus m H2. So for all options, right, otherwise let me write the H2 outside. H2 first, not outside, H2 plus m into H1 minus m into H2. H2, if I write minus m outside, H2 minus H1. Correct, na? Yes. So the H3 will be equal to, let us see it. H3 equal to H2 minus m, H2 minus H1, yes. H3 equal to H2 minus m, H2 minus H1. Therefore, option C absolutely correct. It is also easy problem but quite a lengthy problem, easy only, right? Since it is given, the specific enthalpy of the liquid leaving the heater is equal to, right, means the material, both materials, the blood steam and 1 minus m kg mass of saturated liquid available from condenser are directly mixing. If the blood steam and the condensate both are directly mixing in the feed heater, that is called open feed water heater. That is why I wrote open feed water heater, open feed water heater. Understood? Yes. Now let us take the another question asking like this. Match list 1 with list 2. Steam nozzle, compressible, surface tension, heat conduction. Mach number, reaction turbine, Biot number, Nusselt number, supersaturation, Weber number. Here steam nozzle, supersaturation, A5. Compressible flow, Mach number, B1. Surface tension, Weber number, because heat conduction connected to Biot number. So C6, and D3, that is the correct matching. Understood clearly? Steam nozzle connected to supersaturation flow, compressible flow, Mach number connected to compressible flow, surface tension is surface tension, Weber number, and heat conduction, Biot number connected to heat conduction. So A5, B1, C6, D3 correct. Got it? Yes. Then look at the another question. The isentropic heat drop in the nozzle of an impulse steam turbine with nozzle efficiency given 0.9, blade velocity ratio, that means U by V1 equal to 0.5, and mean blade velocity 150 meter per second, right? Blade velocity U given 150 meter per second. You are asked to decide what is the isentropic enthalpy drop. Remember, this V1 is the actual velocity. This V1 is the actual velocity. For that, from this, what can be written? V1 equal to actual velocity V1 equal to U by 0.5. U 150. 150 divided by 0.5, that is equal to 300. 300, correct na? 300 meter per second. That is the actual velocity. As you know, the actual velocity divided by ideal velocity, I for ideal, actual velocity divided by ideal velocity is the coefficient of velocity. That coefficient of velocity is equal to root over nozzle efficiency. Remember these relations. The ratio between the actual velocity and ideal velocity is the coefficient of velocity. That coefficient of velocity equal to nozzle efficiency, root over nozzle efficiency. From this, the ideal velocity equal to actual velocity divided by root over nozzle efficiency. The actual velocity 300 divided by root over, look at the nozzle efficiency 0.9. You simplify this value for getting the ideal velocity. My calculator has shown 316.23. 316.23 meter per second. That is the ideal velocity. Once again, 316.23. Yes. This ideal velocity equal to 44.72 into root under isentropic enthalpy drop. From this, ideal velocity divided by 44.72 is equal to root over isentropic enthalpy drop. Then isentropic enthalpy drop equal to Vi square, ideal velocity square, divided by 44.72 whole square, right? It is equal to Vi. Look at the ideal velocity 316.23. 316.23 whole square divided by 44.72 whole square. You simplify, right, this value for getting around 50 kilojoules per kilogram. That is the isentropic enthalpy drop, right. 50. Look at the option A. Option A itself is absolutely correct. Understood? Very easy, right? Similarly, look at the last question from the Rankine cycle, asking like this. For a compressible fluid, sonic velocity generally denoted with A. Sonic velocity A equal to root over gamma RT. That is one formula. Another formula, root over dP by d rho. These are the two relations for deciding the sonic velocity or acoustic velocity or sound velocity. Look at the options. A property of the fluid, no, always given by gamma RT power 1 by 2, it is correct, where gamma R and T respectively are the ratio of specific heats, gas constant temperature, B absolutely correct, always given by dou P by dou rho, dP by d rho whole power 1 by 2 absolute, where P and rho are the respectively pressure and density, C also correct, always greater than velocity of the fluid at any, no, always not correct. Anyhow, right, option B and C, B and C are correct. B and C are absolutely correct. That's all about the Rankine cycle questions and solutions. I hope all of you clearly understood. Understood or not? Yes. Thank you. Thank you very much. Dear students, now let us discuss the solutions for very easy unit, that is gas turbines. You know, Brayton cycle is the theoretical cycle for constant pressure gas turbine power plant, whereas Atkinson cycle is the theoretical cycle for the constant volume gas turbine power plant. Constant volume gas turbine power plant means the combustion chamber is constructed for firing the fuel at constant volume, whereas constant pressure gas turbine power plant means the combustion chamber for constant pressure gas turbine power plant is made for burning the fuel at constant pressure. Okay, having that introduction, look at the very first question asked for 1 mark in the year 1994. Look at this one. A gas turbine cycle with infinitely large number of stages during compression and expansion leads to Stirling cycle, Atkinson cycle, Ericsson cycle, Brayton cycle. Dear friends, remember the Ericsson cycle consists of 2 isobaric process and 2 isothermal process. If the Brayton cycle is constructed or gas turbine power plant is constructed with a large number of ideal intercoolers and large number of ideal reheaters, the Brayton cycle is looking like a Ericsson cycle. Therefore, the Brayton cycle efficiency with a large number of ideal reheaters and ideal intercoolers will be equal to Ericsson cycle efficiency, that is equal to Carnot cycle efficiency, because Ericsson cycle efficiency equal to Stirling cycle efficiency equal to Carnot cycle efficiency for the same temperature limits. Okay, it is like this. If you look at the Brayton cycle is having 2 isobaric process and 2 isentropic process. Let this is the pressure after compression P2 and this is the pressure before compression P1. For increasing the pressure from P1 to P2, if I select the large number of compressors with ideal intercoolers, this may be the pressure before compression P1. If I select the large number of stages for compressing the gas with ideal intercooling mechanism, pressures in each stage gradually increasing like this. These are all the ideal intercooler pressures. ideal intercooler pressures. Let us start the compression somewhere here. 1, right. So, first in the low pressure cylinder, gas is compressing isentropically and cooling isobarically to the original temperature. Isentropic compression, isobaric heat rejection in the intercooler. Isentropic compression, isobaric heat rejection, isentropic, isobaric, like this. It is repeating many times. It is repeating many times, right, like this. 1 minute, let me, like this. Those are all the ideal intercooler pressures. Isentropic compression, isobaric heat rejection, isentropic compression, isobaric cooling in the intercooler, isentropic like this. So, it is looking like almost isothermal compression followed by isobaric heat addition, isobaric heat addition. For expansion process, I am selecting large number of stages, right. In between the two stages, the gas is reheating ideally. Reheating ideally means after reheating, the gas temperature reaches to the peak temperature. These are all the intermediate pressures for ideal reheaters. The gas may start its expansion. The gas may start its expansion somewhere here. Isentropic expansion, isobaric heating, right, isobaric reheating, right, to peak temperature. Isentropic expansion, isobaric heating, isentropic, isobaric, isentropic, isobaric, like this. It repeats n number of times. Isentropic, isobaric, isentropic, isobaric, isentropic, isobaric, isentropic, like. So, right, if you select the large number of, many number of ideal reheaters, this 2 to 3 is the heating process in the combustion chamber, 3 to 4 almost isothermal expansion. Isothermal compression, that means the compression with large number of ideal intercoolers looking like isothermal compression, then constant pressure heat addition, and expansion with large number of ideal reheaters looking like isothermal expansion 3 to 4 followed by constant pressure heat rejection. So, it is having 2 isothermal process and 2 isobaric process. The cycle which is having 2 isothermal and 2 isobaric is called Erikson cycle. It is actually, it is originally Brayton cycle, but constructed with a large number of ideal reheaters and ideal intercoolers. Then the cycle is looking like Erikson cycle. Then the Brayton cycle efficiency with a large number of ideal intercoolers and large number of ideal reheaters equal to Erikson cycle efficiency. Erikson cycle efficiency equal to Stirling cycle efficiency is equal to Carnot cycle efficiency for the same temperature limits. That is why I opted the Erikson cycle. It is very, very important point. The Brayton cycle with a large number of ideal intercoolers and large number of ideal reheaters looking like a Erikson cycle. Okay, got that point? Yes. Then look at the next question. It is the 2 marks question asked in the year 89 before 90. It is asking like this: the current level of maximum temperature of steam turbine inlet is much lower than that gas turbine inlet because for the reciprocating type heat engines like petrol engine or diesel engine, the maximum allowable temperature may be around 3000 Kelvin or 3500 Kelvin also. Such a very high temperature you cannot maintain for the gas turbine power plant because perfect cooling can be possible either with a petrol engine or with a diesel engine, either by air cooling mechanism or radiator cooling mechanism called water cooling mechanism. Such kind of cooling mechanism cannot be possible for the gas turbine power plant. That is why the metallurgical limitation, the maximum temperature that we can allow for the gas turbine power plant is less than the maximum temperature what we can maintain for the petrol engine. But if you compare the gas turbine power plant and steam turbine power plant, the maximum allowable temperature for the steam turbine power plant still less than the maximum temperature that you can allow for the gas turbine power plant, because somehow the gas turbine blades can be cooled by utilizing the compressed air. It is like this. If you look at the gas turbine power plant mainly consists of a compressor, rotary type compressor. This compressor takes the air from the surroundings with a pressure P1, temperature T1. Because of the compression, pressure and temperature increase. The pressure after compression is P2. Pressure after compression is P2 and temperature after compression is T2. Assume the temperature of the air with which it is entering to compressor, let it be 300 Kelvin. Because of the compression, temperature may be increased to 500 Kelvin. With this temperature, air is made to enter to the combustion chamber, where the fuel is burning at constant pressure for constant pressure gas turbine power plant. Because of the fuel burning or because of the heat addition at constant pressure, temperature increases. This is the state 3, where the pressure is P2 only, because the heat is supplied or the fuel is burning for constant pressure gas turbine power plant at constant pressure, P2 only, but temperature increases to the peak value. That peak temperature T3 equal to T maximum. That T maximum allowable temperature may be around 1000 Kelvin or 1000 Kelvin or 1200 Kelvin. You can go up to 1500 Kelvin. Assume that is the metallurgical limitation, maximum temperature. With that maximum temperature, the gas is made to expand over the gas turbine blades. The gas is made to expand over the gas turbine blades. This is the gas turbine. By the time the gas is expanding over the turbine blades, that gas is maintaining high temperature. But for the purpose of cooling the gas turbine blades, what we are practically doing is we are extracting a part of the air. We are extracting a part of the air from the exit of the compressor for the purpose of gas turbine blade cooling. That mechanism is called bleeding mechanism. This compressed air is made to pass through the shaft placed between turbine and compressor. That means this shaft is made number of grooves. Through that grooves, the compressed air at 500 Kelvin is made to pass through the grooves made in the blades. Generally, aerofoil type blades are used for the gas turbine power plant. This is the geometric shape of the aerofoil type blade. By the time the gas over the surface is made to expand around at 1000 Kelvin. For the purpose of cooling the gas turbine blades, what we are practically doing is we are making number of holes inside the blade. Through these holes, this compressed air around at 500 Kelvin is made to flow. The compressed air is passing through the grooves made in the blade around at 500 Kelvin, while the combustion products are expanding over the turbine blades at 1000 Kelvin. Because of the temperature difference, right, the gas turbine blade can be cooled. That is how, right, up to some extent the gas turbine blades can be cooled. In case of gas turbine blade cooling mechanism, look at the temperature of the coolant. Temperature of the coolant is very high, whereas for the petrol engine or the diesel engine, the coolant is available as water at 20 degrees centigrade, that is around, right, 293 Kelvin, approximately 300 Kelvin. That means the coolant is available for the reciprocating heat engine like petrol engine at 300 Kelvin, whereas coolant available for the gas turbine blade cooling at 500 Kelvin. Since the coolant is available at high temperature, right, we cannot allow for very high temperature at the inlet of the gas turbine, like how you can maintain very high temperature for the reciprocating heat engine. This is the practical reason why the why the high temperature cannot be maintained at the inlet of the gas turbine, right, in comparison to the reciprocating heat engine, that is petrol engine or diesel engine. That means if you compare the petrol engine, reciprocating type petrol engine and gas turbine power plant, the maximum allowable temperature for gas turbine power plant is less. But if you compare the steam turbine power plant and gas turbine power plant, this kind of blade cooling, the steam turbine blade cooling is not possible. That's why the maximum allowable temperature for the steam turbine is low compared to that of gas turbine power plant, right? So that is the right explanation. Now look at the options. Let me read the question once again. The current level of the maximum temperature of the steam turbine inlet is much lower than that of gas turbine inlet, because the fuel combustion temperature in a steam generator is lower than that in a gas turbine engine. Absolutely wrong. Of the corrosive nature of the high temperature steam on superheater tubes. Absolutely wrong. The material used for the gas turbine blades are not suitable for the steam turbine blades. That is also not correct answer. Unlike the gas turbine blades, the steam turbine blades cannot be cooled. Absolutely correct. Up to some extent, gas turbine blades can be cooled by extracting a part of the air from the exit of the compression. That means this compressed air, a part of the compressed air is used as a coolant for the purpose of gas turbine blade cooling. Such kind of facility cannot be available for the steam turbine power plant. That's why maximum allowable temperature for the steam turbine power plant is less compared to that of gas turbine power plant. I hope all of you clearly understood. Understood or not? Yes. Then let me take the another question. Look at this one. It is asking like this. In a gas turbine power plant, intercoolers are used to cool the intercoolers are placed between the two stages of compression. Therefore, the intercoolers are used for cooling the compressed air. Intercoolers are for cooling the compressed air in order to decrease the compression work. By the time the gas is cooled between the two stages, right? When you place the intercooler, it is like this. Let us take, this is the low pressure compressor. Low pressure compressor. For this low pressure compressor, gas is entering with a pressure P1, temperature T1. That gas is compressing in the low pressure compressor to increase the pressure from P1 to P2. By the time the pressure is increasing, temperature also increasing from T1 to T2. Now, before this gas is made to enter to the another compressor, the gas is cooled by placing a heat exchanger called intercooler. That intercooler is constructed for working or for dumping the heat from compressed air to coolant at constant pressure. Therefore, 2 to 3, I can say 2 to 3 is a constant pressure process. At constant pressure, according to Charles' law, volume is directly proportional to absolute temperature. Because of the rejection of the heat from the compressed air, temperature of the air decreases. When the temperature of the air is decreasing, volume occupied by the air is decreasing. That means indirectly, because of the cooling the gas between the two stages, the gas is made to enter to the high pressure compressor at or with low specific volume. Then what is the work required for the compressor? Work required for high pressure compressor specifically equal to VDP. Of course, for low pressure compressor also VDP, because we are treating that the compressors are steady flow devices. Because of the cooling the gas in the intercooler, that is in between the two stages, the gas is indirectly made to enter to the high pressure compressor with a low specific volume. When the V in the VDP work is decreasing, definitely compression work is decreasing. So the main intention of cooling the compressed air between the two stages is for reducing the compression work. Once again, in a gas turbine power plant, intercoolers are used to cool the compressed air in order to decrease the compression work. That is the answer. Understood clearly? Yes. Then look at the next one. It is asked in the year 1993 like this. air expands steadily through a turbine from 6 bar 800 Kelvin to 1 bar 520 Kelvin. During the expansion, heat transfer from the air to the surroundings at 300 Kelvin is 10 kilojoules per kg of air. Neglecting changes in kinetic energy and potential energies and evaluate the irreversibility per kg of air. Assume air to behave as an ideal gas. For that ideal gas Cp given, R value also given. You are asked to decide irreversibility. As you know, irreversibility I equal to T naught into net entropy change. That is the entropy change of the universe. T naught into net entropy change means entropy change of the system plus entropy change of the surroundings. Entropy change of the surroundings. Since the heat is transferred from air to surroundings at 300 Kelvin, surroundings are receiving the heat energy with a magnitude 10 kilojoules per kg. Therefore, the entropy change in the surroundings equal to del Q dividing by T surroundings. Okay. Since the surroundings are receiving heat energy, thermodynamically heat receiving is taken as positive. That del Q is plus 10 divided by 300. That is the entropy change in the surroundings. Then you need to decide the entropy change of the system, that is entropy change of the gas during the expansion process. For that, it is better to mark the TS diagram, temperature versus entropy diagram. You know, it is given for gas turbine power plant. Gas turbine power plant consists of two pressure limits: pressure before compression, pressure after compression. Let me complete the cycle with irreversibilities. 1 to 2 isentropic compression. Of course, nothing is spoken regarding the compression, right? If I consider the irreversibilities during the compression, 1 to 2 dash is the actual compression. Then heat is supplied at constant pressure, 2 to 3 or 2 dash to 3 isobaric heat addition. If the gas is expanding ideally in the turbine, 3 to 4 is the isentropic expansion, that is the reverse adiabatic expansion. But once I consider the irreversibility effect, the entropy is going to increase. The expansion curve is deviating from 3 to 4 to 3 to 4 dash. That means 3 to 4 ideal expansion, 3 to 4 dash is the actual expansion in the turbine. Now look at the pressures. Air expands steadily through a turbine from 6 bar 800 Kelvin. That means at state 3 pressure is 6 bar. Let me write it clearly. And temperature is T3. What is that T3? T3 800 Kelvin. 800 Kelvin. It is expanded to 1 bar and 520 Kelvin. Expanded to 1 bar means P1 equal to 1 bar. And what about that 520 Kelvin? Is it the temperature at state 4 or 4 dash? 4 dash. Remember, the temperature or the data which is given in the problem always actual data. Therefore, T4 dash given, that T4 dash given as 520 Kelvin. 520 Kelvin. Okay, right. During the expansion, heat transfer. Okay. Then, now let us decide the entropy change. Entropy change of the system. System means here gas, expanding gas, equal to Cp ln T3 by T4 dash minus R into ln pressure at state 3. Pressure at state 3 is P2 only, right? Pressure at state, okay, here it is, no, 1 minute. I should take the, right, temperature ratio and pressure ratio with respect to, that means 1 minute, let me write it clearly. This is nothing but entropy change of the system is nothing but S4 dash minus S3. S4 dash minus S3. It is equal to Cp ln T4 dash divided by T3 S4 dash, right? Final state temperature by initial state temperature minus R ln the state 4 dash temperature P4 dash by P3. That is the formula. Cp given. How much it is given? Cp1 or 0.3. 1.0 ln. Look at the T4 dash 520 divided by T3 800 minus R value 0.3 ln P4 dash, pressure at state 4 dash is 1 bar divided by 6. That is the entropy change of the system. Then what is the irreversibility? Irreversibility I equal to, irreversibility, let me change the color of the marker, color of the pen. Irreversibility I equal to T naught into entropy change of the system, entropy change of the system plus entropy change of the surroundings, entropy change of the surroundings. Close the bracket. T naught means dead state temperature, that is surrounding temperature 300 into, look at the entropy change of the system, right? Here it is 1.0 into ln 520 divided by 800 plus minus this part 0.3 ln 1 by 6, that is the entropy change of the system plus entropy change of the surroundings, already you have decided 10 by 300. You simplify it for getting the irreversibility. My calculator has shown the value, directly I am writing the value 42.04 kilojoules per kilogram. That is the loss of available energy or irreversibility due to friction effect. Understood clearly? That is what he is asking. Neglect the changes in kinetic energy and potential energy and evaluate the irreversibility per kg of the air. Okay, that is the answer. Okay, 42.04. So answer I got is 42.04 kilojoules per kilogram. Okay. The another part of the same problem is like this. In the previous problem, find the actual work and maximum work. Maximum work is means ideal work. Ideal work is with ideal process Cp T3 minus T4. Cp T3 minus T4. Actual work equal to what? Work for 3 to 4 dash process. It is equal to Cp into T3 minus T4 dash. Okay. It is equal to 1 into T3 given 800 minus 520. This is the actual work. My calculator has shown the actual work is 280 kilojoules per kilogram. For deciding the ideal work, I should find the T4. How do you decide the T4? Look at the, right, 3 to 4 process. For the 3 to 4 process, T4 equal to T3 by Rp power gamma minus 1 by gamma. T3 800 by Rp, right, Rp equal to 6, right, 6 power 0.4 by 1.4. Here Rp means pressure ratio. Rp actually P2 by P1. P2 by P1. You simplify that value for getting the T4. My calculator has shown 479.47. 479.47 Kelvin. So by using the T4, I can decide the ideal work. So the ideal work, maximum work or ideal work equal to Cp 1 into T3 800 minus 479.47. 479.47. It gives the maximum possible work from the turbine. That maximum possible work is 320.53. 320.53 kilojoules per kilogram. That is the maximum possible work. I hope all of you clearly understood. Lengthy problem, easy only, but lengthy problem. Understood or not? Yes. Then let me take the another question. A gas turbine cycle with heat exchange and reheating improves. With heat exchange means regeneration mechanism. With regeneration mechanism, gas turbine power plant efficiency increases. Wherever you go for the regeneration, whether that is steam turbine power plant or gas turbine power plant, regeneration mechanism always increasing the efficiency. The reheating for the gas turbine power plant is increasing the net work output of the power plant. Dear friends, remember, the reheating mechanism not only increasing the net work output of the gas turbine power plant, but also the gas available from the exit of the gas turbine with reheating maintaining high temperature. That very high temperature gas is more effectively can be used for the regeneration purpose. That means indirectly, because the reheating cycle is best suitable for regeneration, because the gas available from the exit of the gas turbine with reheating mechanism is maintaining high temperature. If I send that high temperature gas for the regenerator, the compressed air temperature can be increased to maximum value before it is entering to combustion chamber. Therefore, the heat input to the combustion chamber decreases. Anyhow, the gas turbine power plant, if the gas turbine power plant is constructed with a combination of regenerator and reheating, not only increasing the thermal efficiency but also increasing the specific work output. Both thermal efficiency and specific work output both are improving. Option C, absolutely correct. Okay, understood clearly? Yes. Then see, dear friends, remember, if you take the combination of intercooling regeneration and combination of reheating regeneration, combination of reheating and regeneration can maintain the better efficiency than the combination of intercooling and regeneration, because with the reheating cycle, the exhaust gas available from the exit of the turbine maintaining high temperature. Therefore, that high temperature gas more effectively can increase the temperature of the compressed air when that high temperature gas is sent to the regenerator, right? So it is like this, right? So when you take the 1 minute, listen carefully. Let me take the turbine inlet temperature on the x-axis, thermal efficiency on the y-axis. When you keep on increasing the turbine inlet temperature, for the simple Brayton cycle, efficiency increases like this. that is marked as A. But if the regeneration mechanism is arranged, the efficiency is increased in the better manner, that is B. If the combination of intercooling and regeneration is used, combination of intercooling and regeneration is used, this is how thermal efficiency increases. If the combination of reheating and regeneration is used, this is how the efficiency increases. If you go for combination of intercooling, reheating and regeneration, that is how the efficiency increases. That means A, the curve A is for simple Brayton cycle, B is for the Brayton cycle with intercooling, that means Brayton cycle with regeneration. A, let me write it, A for simple Brayton cycle, simple Brayton cycle. B is for regeneration cycle, regeneration cycle. C is for combination of intercooling and regeneration. Next, D is for combination of reheating and regeneration. From that you can conclude that combination of reheating and regeneration can maintain better efficiency than combination of intercooling and regeneration. Whereas E for the combination of reheating, intercooling and regeneration. I hope all of you clearly understood. Understood or not? That is how thermal efficiency increases. With increase in TIT, means turbine inlet temperature. Okay, na? Shall I take next one? Yes. Look at the last question from the gas turbine power plants. Asking like this: select statements from list 2 matching the process in list 1. Enter your answer as A, B if the correct answer for 1 is A and that for 2 is B. Okay. Look at the list 1. Intercooling, isothermal compression. No heat transfer during the compression. No heat transfer during the compression means that is the adiabatic compression. Reduce the low pressure compression work. Heat rejection during the compression. This heat rejection during the compression can be connected to isothermal compression. Heat rejection during the compression connected to isothermal compression, because you know in general during the compression process pressure increases. Along with pressure, temperature is supposed to be increased. But if you want to maintain constant temperature during the compression, that is for isothermal compression, means to maintain the constant temperature during the compression, you must add the cold source. Once we add the cold source, the compressing gas can dump the heat to the cold source. By the time the compressing gas is dumping the heat to the cold source, temperature of the gas decreases. It is like this. Let us take the bicycle pump. Let us take the bicycle pump. This is the cylinder, piston, right? I am applying the force on the piston. Then whatever the gas or air is there inside the cylinder, that gas is compressing by the time the piston is pushing down. During the compression process, pressure increases, but general nature of the gas is that by the time the pressure is increasing, temperature also increases. But if you want to maintain the constant temperature, what you do is you place this bicycle pump in a bucket of cold water. That cold water present in the bucket is acting as a cold source. That means by the time the gas is compressing, pressure increases, along with the pressure temperature increases. That means this gas or air inside the cylinder maintains high temperature than the cold source, then that compressing gas is dumping the heat to cold source. Because of the dumping the heat to cold source, temperature of the gas decreases. Then combined effect of gain in temperature due to increase in pressure by compression and a drop of temperature due to cold source, this combined effect may maintain a constant temperature. From that the conclusion is cold source is the counter effect for isothermal compression. For that I have selected, right, the isothermal compression is possible by rejecting the heat during the compression. Isothermal compression is possible by dumping the heat to the cold source. That's why, right, that is marked 2C correct. 2C correct. Okay. Now, intercooling reduces high pressure compression work. Yes, that already we discussed in the first problem, right? So, intercooling 1D. Intercooler is decreasing the, in the intercooling mechanism at constant pressure, volume is directly proportional to temperature. Because of the cooling the gas in intercooler, the temperature decreases, the volume occupied by the gas decreases because volume is proportional to temperature. Then what is the work required for the high pressure compressor? Work required for high pressure compressor equal to VdP. Because of the cooling the gas, before the gas is entering to high pressure compressor, volume of the gas is less, then the V in the VdP work is decreasing. When the V in the VdP work is decreasing, high pressure compressor is demanding the less work. Therefore, intercooling connected to reducing the high pressure compression work. Anyhow, 2C, 1D absolutely correct. I hope all of you clearly understood. Understood or not? Yes. That's all about the problems from the gas turbine power plant. Okay? Na? Yes. Thank you. Dear students, now let us discuss the solutions for the refrigeration. Before 2000, the weightage for the refrigeration was very less, but now, right now, compulsory you can expect 2 marks question in the gate from the refrigeration part. With that introduction part, look at the first question asked for 1 mark in the year 2000. In a vapor compression refrigeration system, liquid to suction heat exchanger is used to. In a vapor compression refrigeration system, liquid to suction heat exchanger is used to. If you take the vapor compression refrigeration system, the vapor compression refrigeration system consists of a compressor. This is the compressor. This is the compressor. Condenser, where the heat is rejected. This condenser in our domestic refrigerator, water cooler, window AC units, these are all working by vapor compression refrigeration system. Anyhow, in our domestic refrigerator, you can practically find the condenser at the back of the refrigerator. It is made in the form of mesh coated with black powder. That is called condenser. Throttle valve called capillary tube, throttle valve, and evaporator. In our refrigerator, the deep freezer is the evaporator. Deep freezer is the evaporator. This is the place where we are placing the working stuff. That is the place where we are placing the working stuff. From that working stuff, the circulating refrigerant is extracting the heat to maintain the low temperature. Let me complete the cycle. The cycle can be completed like this. Listen carefully. the working fluid used in the refrigeration system is called refrigerant. For vapor compression refrigeration system, generally either CFC refrigerant, that is chlorofluorocarbon kind of refrigerant, or HFC, hydrofluorocarbon kind of refrigerant is used. Whenever you supply the power to the compressor, this compressor draws the refrigerant from the evaporator in the form of vapor state. That means whenever you supply the electric energy to the compressor of your domestic refrigerator, that compressor draws the refrigerant from the evaporator in the form of vapor. Assume that vapor is maintaining the pressure P1, enthalpy H1. Because of the compression, definitely pressure increases. By the time the pressure is increasing, temperature also increases. With the temperature, the refrigerant is entering to condenser where the coolant is available. For that coolant, refrigerant is dumping the heat. By the time the refrigerant is dumping the heat, the vapor is becoming saturated liquid. Vapor is becoming saturated liquid. That saturated liquid, once again, the vapor refrigerant which is available from the compressor is entering to condenser where the heat is rejecting. Because of the heat rejection, vapor refrigerant is becoming saturated liquid refrigerant. That saturated liquid refrigerant is expanding in the throttling device like capillary tube. In the throttling device, right, both pressure and temperature both are decreasing. The pressure at state 3 is P2 only because condensation is happening at constant pressure, but temperature is decreased to T3. Temperature decreased to T3. In terms of enthalpy also I can write. Enthalpy at state 2 is H2, enthalpy at state 3 is H3. With this pressure and temperature, the liquid refrigerant is throttling. During the throttling process, pressure decreases. Along with the pressure, pressure may be decreasing from P2 to P1. Along with the pressure, temperature is decreasing from T3 to T4. But enthalpy remains constant because throttling process is maintaining constant enthalpy. That's why throttling process can also be called as isenthalpic process. Though I write here H4, enthalpy at state 4 H4, that H4 equal to H3 only. With this low pressure and low temperature, the liquid refrigerant is entering to evaporator for extracting the heat from working stuff. By the time the liquid refrigerant is extracting the heat from the working stuff, the liquid refrigerant is becoming vapor refrigerant. The same vapor refrigerant is returned to compressor. Then the same cycle will be repeated again and again. The same cycle will be repeated again and again. By the time the refrigerant is continuously circulating, due to rejecting the heat to the refrigerant from the working stuff, the working stuff is maintaining low temperature. That is how we are maintaining the refrigerator cabin temperature is around 5 degrees centigrade. That is the temperature we are setting for our refrigerator cabin. That means the liquid refrigerant, while it is taking the heat from the working stuff, liquid refrigerant is becoming vapor refrigerant. Then the working stuff is provided and maintained low temperature 5 degrees centigrade. Anyhow, assume the vapor which is available from the evaporator is maintaining the temperature. Refrigerant is maintaining 5 degrees centigrade. Definitely vapor must be maintaining the working stuff, not refrigerant. The working stuff is maintaining 5 degrees centigrade. For transferring the heat from the working stuff to refrigerant must be maintaining low temperature. The temperature maintained by the refrigerant while it is evaporating is the saturation temperature. let that saturation temperature 2 degrees centigrade. That means if the saturated vapor is available, from the evaporator corresponding to P1 temperature 2 degrees centigrade may be the saturation temperature. With that saturation temperature, the vapor refrigerant is entering into compressor. Because of the compression, pressure increasing. Along with the pressure, temperature may be increased to around 80 degrees centigrade. During the compression process, by the time the pressure is increasing, temperature is increasing from T1 to T2. With this high pressure and high temperature, refrigerant is entering to condenser, where the refrigerant is dumping the heat. Once the vapor refrigerant which is in saturation state is entering to compressor, definitely saturated vapor is becoming superheated vapor. That superheated vapor temperature is 80 degrees centigrade. But corresponding to P2 temperature, let the saturation temperature, corresponding to P2 temperature, saturation temperature may be 40 degrees centigrade. It means by the time the refrigerant is rejecting the heat to the coolant available in the condenser, the temperature of the refrigerant is dropping from 80 degrees centigrade to saturation temperature corresponding to P2. Once its temperature is dropped to saturation temperature, then the kind of heat rejection is called latent heat. During the latent heat transfer, no temperature change. It means indirectly the saturated liquid is available with 40 degrees centigrade. That is not exact value, that is not standard value, right? For your better understanding, I have taken that value. That means the superheated refrigerant is entering to condenser. That superheated refrigerant is becoming saturated liquid refrigerant. By the time the superheated refrigerant is dumping the heat, it is dropping its temperature from superheat temperature to saturation temperature. Once it reaches to saturation state, because of the further latent heat rejection, no temperature change. With this low temperature, refrigerant is entering to throttling device, where the temperature is dropping from 40 degrees centigrade to T4, let it be 2 degrees centigrade. At this temperature, it is extracting the heat from the working stuff, whatever you placed in the evaporator. From that, the moral is, by the time the throttling is happening, though the enthalpy remains constant, there is a possibility to drop the temperature from this temperature to this temperature. Okay, understood that point? Then the TS diagram for this arrangement like this. It consists of only two pressure limits. Let me take the temperature versus entropy diagram. The saturation dome, that is how the saturation dome is appearing. With the TS coordinate system. Pressure before compression is P1. This is the pressure before compression P1. Pressure after compression is P2. We are assuming that saturated vapor is entering to compressor. Then you try to mark the point, right, on the P1 exactly at saturated vapor state, because we are assuming that saturated vapor refrigerant is entering to compressor. Wherever the P1 is meeting the saturated vapor curve, that is the state of the refrigerant while it is entering to compressor. By the time the saturated vapor refrigerant is compressing, the saturated vapor refrigerant is becoming superheated refrigerant. That is the 122 isentropic compression. This saturation temperature, according to our assumed values, saturation temperature is 2 degrees centigrade. By the time the refrigerant is compressing, temperature increases to 80 degrees centigrade. That means at state 2, the temperature is T2, that is 80 degrees centigrade. That is assumed value, that is not standard value. Since we are assuming saturation temperature corresponding to P2 is 40 degrees centigrade, this is the saturation temperature corresponding to P2. That is equal to 40 degrees centigrade, that is assumed value only. With this superheated state, refrigerant is entering to the condenser. By the time the refrigerant is dumping the heat to the coolant available in the condenser, initially refrigerant will be desuperheated. Refrigerant will be desuperheated means its temperature is dropping from superheated temperature to saturation temperature. Once it reaches to saturation state, right? The kind of heat transfer is latent heat. The latent heat is happening at constant temperature. That means once the refrigerant desuperheating is completing, it can maintain the constant temperature. That means the superheated refrigerant is becoming saturated liquid refrigerant. That saturated liquid refrigerant is entering to throttling device where the frictional pressure drop is happening. Pressure is dropping due to friction. Because of the frictional pressure drop, entropy is going to increase. This is a 3 to 4 process. 3 to 4 irreversible adiabatic process. Irreversible adiabatic steady flow process. Anyhow, in the throttling process, enthalpy remains constant, that is H4 equal to H3. Got that point? So, this is the TS diagram. This is the TS diagram for the ideal vapor compression refrigeration system. Ideal vapor compression refrigeration system means refrigerant is entering to compressor under saturation state. Now, right, our point is, look at the temperature of the refrigerant while it is leaving from the evaporator. By the time the refrigerant is leaving from the evaporator, refrigerant is maintaining 2 degrees centigrade temperature. And what is the saturated liquid temperature available? What is the saturated liquid temperature available at the exit of the condenser? 40 degrees centigrade. That means though this is the liquid, it is maintaining high temperature. Though this is the vapor, maintaining low temperature. Then when you place the heat exchanger, for these two states of the same material, this liquid refrigerant can dump the heat to the vapor refrigerant. By the time the saturated liquid refrigerant is dumping the heat to the vapor refrigerant, the saturated liquid refrigerant is becoming subcooled liquid refrigerant. On the other hand, by the time the saturated vapor is extracting the heat from the saturated liquid, its temperature increases. That means the saturated vapor is becoming superheated vapor. That means when I connect the heat exchanger between the saturated liquid available at the exit of the condenser and saturated vapor available at the exit of the evaporator, the saturated liquid is becoming subcooled liquid and saturated vapor is becoming superheated vapor, like this. Let us take the one second diagram. This is the compressor. Listen carefully. This is the compressor. This is the compressor. For this compressor, we are assuming that initially the saturated refrigerant is available at state 1 with a pressure P1, temperature T1 equal to 2 degrees centigrade. We are assuming when the saturated vapor is available. That refrigerant is compressing in the compressor. Because of the compression, temperature increases. The temperature at state 2, we are assuming T2 and pressure at state 2 is P2. This T2 we marked as 80 degrees centigrade. Listen carefully. That T2 is marked as T2 equal to 80 degrees centigrade. By the time the superheated vapor refrigerant is dumping the heat to the coolant available in the condenser, the superheated vapor refrigerant is becoming saturated liquid refrigerant. Here saturated liquid refrigerant is available. Though this is the liquid, maintaining the pressure P2 only, but temperature is Tsat corresponding to P2, that we marked as 40 degrees centigrade. 40 degrees centigrade. Now this is the evaporator. From this evaporator, vapor refrigerant is available. Saturated vapor refrigerant is available with a temperature 2 degrees centigrade. Then I am placing a heat exchanger. Between the saturated liquid and saturated vapor. This saturated vapor is entering to the heat exchanger, right? This is the heat exchanger. This is also called liquid vapor regenerator. Though this is the saturated vapor, that saturated vapor is maintaining low temperature. On the other hand, the saturated liquid is made to enter. This is the saturated liquid available at 40 degrees centigrade. Then both fluids are traveling in the opposite direction, that is the counter direction. Both fluids are traveling, both fluids are traveling in the counter direction. 1 minute. Let me draw it clearly. Both fluids are traveling in the counter direction. That means liquid refrigerant is going up according to our diagram, vapor refrigerant is coming down. There is a temperature difference because the liquid is available at 40 degrees centigrade while the vapor is traveling in opposite direction 22 degrees centigrade. Because of that temperature difference, some heat is transferring from high temperature saturated liquid to low temperature saturated vapor. Then once the saturated liquid is dumping the heat to the vapor, the saturated liquid is becoming subcooled liquid. So the subcooled liquid, this is the subcooled liquid. That subcooled liquid is made to enter to the throttling device. This is the throttling device. This is the throttling valve. For the throttling valve, the subcooled liquid is entering. That subcooled liquid is throttling because of the throttling, right? Because of throttling, pressure and temperature both are decreasing. With that very low temperature and very low pressure, that liquid refrigerant is entering to evaporator for extracting the heat. On the other hand, this saturated vapor is becoming superheated vapor. Then the vapor temperature after the heat exchanger may be maintaining 20 degrees centigrade. Any temperature above saturated temperature is coming under superheat temperature. Since 2 degrees centigrade is the saturated temperature of the saturated vapor, this 20 degrees centigrade is coming under superheated temperature. On the other hand, the liquid temperature may be dropped to around 25 degrees centigrade. Right? Now look at the states. Let me take the new states. 3 to 3 dash. 3 to 3 dash is the subcooling mechanism. This is the state 4 as usual. And this is the this is the 1 we are assuming. This is the 1. This is state 1. Right? 1 to 1 dash. Here I should change the state. Right? This is the 1 dash. That means when I connect the heat exchanger between the saturated vapor and saturated liquid, not only saturated liquid is subcooling, but also saturated vapor is superheated. Because of the combined effect, the TS diagram is looking like this. Listen carefully. The temperature versus entropy. The saturation dome is looking like this. Let me mark the two pressure limits. Pressure before compression, this is the pressure before compression, P1. And pressure after compression, P2. Now, for the previous cycle, look at the previous cycle started here. 1 to 2 is the compression. 2 to 3 condensation. 3 to 4 throttling. That should be drawn by a broken line. 3 to 4 throttling process. 4 to 1 evaporation. But because of the liquid vapor regeneration, the saturated liquid is becoming subcooled liquid at constant pressure. That means this heat exchanger is constructed for working at constant pressure. The saturated liquid is becoming subcooled liquid. Therefore, that subcooling effect should be marked along the constant pressure line. 3 to 3 dash is the subcooling effect. Then it is expanding to this one, 4 dash. By the time the saturated liquid is becoming subcooled liquid, the saturated vapor is becoming superheated vapor. That means combined effect of subcooling of the saturated liquid refrigerant and superheating of the saturated vapor refrigerant both are taking place when you arrange the liquid vapor regenerator. Then the compression is proceeding to 2 dash. That should be vertical line. That is how the refrigerant can be made to enter. To the evaporator under subcooled state. Once the refrigerant is made to enter to the throttling device, not evaporator, once the refrigerant is made to enter to the throttling device under subcooled state, definitely refrigeration effect is going to increase. As you know, area below the TS diagram is the heat transfer. How much amount of extra heat can be, taken by the refrigerant in the evaporator? This 4, right? Let it be K, L. The extra heat taken by the refrigerant in the evaporator equal to area 4 dash K L. This much amount of extra heat can be taken, right? Anyhow, this hatched part is representing increase in refrigeration effect. Increase in refrigeration effect. Okay, but remember, right, this part is not coming under increase in refrigeration effect, because this temperature rise is happening in the heat exchanger, not in the evaporator. The refrigeration effect is increased only in the evaporator. This is the superheating of the refrigerant happening outside the evaporator, that is in the heat exchange. That's why this part of, right, heat transfer, this part of the heat transfer is not at all coming under increase in refrigeration effect. Anyhow, because of the combined effect of subcooling and superheating of saturated liquid refrigerant and superheating of saturated vapor refrigerant, by connecting a heat exchanger between the saturated liquid and saturated vapor, definitely refrigeration effect increases. Therefore, the performance of the system will be better. So, having this information, let us go back to our question. In a vapor compression refrigeration system, liquid to suction vapor heat exchange, keep the COP constant, prevent the liquid refrigerant from the entering the compressor, subcooling the liquid refrigerant leaving the condenser, subcool the vapor refrigerant from the evaporator. No, subcooling the liquid refrigerant leaving from the condenser, right? So, that is the correct option. Because of the subcooling, definitely refrigeration effect is going to increase. So, by the combined effect of subcooling of the saturated liquid refrigerant and superheating of the saturated vapor refrigerant, by connecting just a heat exchanger between the two flows, definitely the refrigeration effect increases and performance increases. That is the correct option. Okay. Now, look at the next question. Global warming is caused by ozone? No. Carbon dioxide? Absolutely correct. Global warming is caused by carbon dioxide. Very simple question, right? Asked in the year 2000. Similarly, look at the 2 marks question asked in the year 92. It is like this. A refrigeration compressor designed to operate with R22 can or cannot be operated with R12 because the condensing pressure of R22 at any given temperature is higher or lower than the R12. Dear friends, remember, a particular compressor is designed based on the characteristics of the refrigerant. Like how you cannot use the diesel in the petrol engine. Similarly, petrol cannot be used for the diesel engine. The same way, the compressor which is made for R22 is not preferable or is not suitable for the R12. If I use the R12 refrigerant, the system may not be properly working because of the difference in condensation pressure. The condensation pressure of R22 is very high compared to condensation pressure of R12. Anyhow, the conclusion is a refrigeration compressor designed to operate with R22 cannot be operated with R12 because the condensing pressure of R22 at a given temperature is higher than the condensing temperature of R12. That is the answer. Understood clearly? Yes. Then look at the next one. The use of refrigerant R22, Freon 22 for the temperature below minus 30 degrees centigrade is not recommended because of high condensation pressure. When the condensation pressure is high, definitely the condensation temperature is high or discharge temperature is high. Look at the options. Good miscibility with lubricating oil? No. Poor miscibility? Also no. low evaporate temperature, also know high compressor discharge temperature. So, the condensation temperature of R22 is high. When the condensation temperature is high, the condensation pressure of the R22 is very high compared to R12. When the condensation pressure is high, condensation temperature is high, that is the meaning of high compressor discharge temperature. Option D can be selected. Okay? Yes. Similarly, look at the last question from the refrigeration part, asking like this, very simple question. Clearance volume of a reciprocating compressor is 100 milliliters. Clearance volume is VC, 100 milliliters. And volume of the cylinder at the bottom dead center, that means total volume. Total volume when the piston is at bottom dead center, this is the cylinder. When the piston is at bottom dead center, this is the bottom dead center. Then this is the volume called total volume. Total volume. That total volume is given as 1 liter. 1 liter. That 1 liter equal to 1000 milliliters. 1000 milliliters, because clearance volume is given in milliliters. Then clearance ratio of the compressor. Very simple. Right, clearance ratio RC equal to ratio between the clearance volume and swept volume. Right, clearance volume by swept volume means piston displacement volume. Even if the piston reaches to top dead center, even after the piston reaches to top dead center, there is a gap between the cylinder cover and piston. That gap is called clearance volume. No reciprocating device can be constructed without clearance volume. If there is no clearance volume, what is happening? Continuously piston is hitting the cylinder cover. Within 1 hour, life will be gone. For that, all reciprocating systems, whether that is for power developing system or power consuming system, there must be some clearance volume. Therefore, this is the piston displacement volume. This is the piston displacement volume. That piston displacement volume technically called as swept volume. That swept volume is equal to what? Total volume. Total volume minus clearance volume. It is equal to clearance volume 100 milliliters divided by total volume is 1000 minus 100. It is equal to 100 dividing by 900. It is equal to 1 by 9. That is the clearance ratio for this particular problem. Look at the option C. Option C is absolutely correct. I hope all of you clearly understood. Understood or not? Yes. Thank you. Dear students, now let us discuss the solutions for internal combustion engines. Okay. First, let us take the 1 mark questions. Look at the question asked in the year 1998. It is given like this: with increasing temperature of intake air, IC engine efficiency. You know, the IC engines may be either petrol engines or diesel engines. Petrol engines are working on Otto cycle, whereas diesel engines are working on diesel cycle. For both cases, look at the petrol engine cycle, that is Otto cycle, efficiency equal to 1 minus 1 by RC power gamma minus 1. Whereas diesel engine efficiency, which is working on diesel cycle, O for Otto, diesel, equal to 1 minus 1 by RC power gamma minus 1 into K. I can write here K, where K equal to rho power gamma minus 1 by gamma into rho minus 1. Here rho is not connected to the temperature of the intake air. There is no dependency or there is no relation between the cutoff ratio rho and intake temperature of the air. Therefore, K is constant. Since K is constant, for both cases I can say that efficiency is completely depending on the RC, compression ratio. Now, if compression ratio is more, not only petrol engine can maintain, better efficiency, but also diesel engine can maintain better efficiency. For that, let us see whether the compression ratio can be increased or decreased when the intake temperature of the air is increasing. For that, as you know, T2 by T1, for both Otto cycle and diesel cycle, very first process is isentropic compression. For isentropic compression, relation between the temperature and volume is T2 by T1 equal to V1 by V2 power gamma minus 1. Let me mark the PV diagram. For the very first process, that is isentropic compression for both Otto cycle and diesel cycle, this is the representation of isentropic compression. Let me change the color of the pen. Look at the representation of isentropic compression. This is the representation of isentropic compression for both Otto cycle and diesel cycle. By the time the air inside the cylinder is compressing, temperature is increasing from T1 to T2, while the volume is decreasing from V1 to V2. Then the relation between temperature and volume is T2 by T1 equal to V1 by V2 power gamma minus 1. But generally the quantity V1 by V2, that is volume before compression by volume after compression, is called as compression ratio. That compression ratio is marked with RC. T2 by T1 is equal to RC power gamma minus 1. RC power gamma minus 1. From this, compression ratio equal to T2 by T1 power 1 by gamma minus 1. Now, here it is given that when the intake temperature of the air is increasing, when T1 is increasing, RC is decreasing. For the same T2, nothing is spoken regarding the T2. When the intake temperature of the air is increasing, compression ratio decreases. When compression ratio decreases, efficiency, is it increasing or decreasing? Decreasing. Yes. Option A itself is absolutely correct. With increasing temperature of the intake air, IC engine efficiency decreases. Option A is absolutely correct. Understood clearly? Yes. Then let me take the 2 marks questions. This is a question asked in the year 90. Given like this, the power output from a spark ignition engine varied. For a spark ignition engine, the air fuel mixture is supplied to the cylinder from the carburetor. That air fuel mixture will be deciding the power output. Changing the ignition timing? No. Regulating the amount of air fuel induced? No. Regulating the amount of air fuel mixture? By regulating the amount of air fuel mixture, power output can be controlled. The power output from the spark ignition engine is varied by regulating the amount of air fuel mixture. Option C can be selected. Okay. Regulating the amount of fuel, regulating the amount of air fuel mixture, regulating the amount of air fuel inducted, air fuel mixture, C can be selected. Option C is absolutely correct. Okay. Similarly, look at the next one. For determining the ignition quality of compression ignition engine fuels, for compression ignition engine means diesel engine. For diesel engine, diesel is the fuel. The quality of the diesel fuel, right? The reference fuel, the quality of the diesel fuel is measured by cetane number. That cetane number, right? For the cetane number, the reference fuels are cetane and alpha methyl naphthalene. That means the quality of the cetane for the diesel fuel is measured in terms of cetane and alpha methyl naphthalene, whereas the quality of the petrol for the petrol engine is measured, right, by octane number. For deciding the octane number, reference fuels are isooctane and N-heptane. That means for the petrol engine, that is also called spark ignition engine. For the petrol engine, the octane number is deciding the quality of the petrol. That octane number is decided by two reference fuels, that is isooctane and N-heptane. Whereas the diesel is the fuel for diesel engine. The quality of the diesel for diesel engine is decided by cetane number. The reference fuels for deciding the cetane number for diesel engine, the reference fuels for deciding the cetane for diesel of the diesel engine, cetane and alpha methyl naphthalene. Since it is given for compression ignition engine, means diesel engine, for diesel engine, diesel is the fuel. For the diesel as fuel, the reference fuels for deciding the cetane number is cetane and alpha methyl naphthalene. Option B is absolutely correct. Understood clearly? Yes. Then look at the next one. If air fuel ratio of the mixture in petrol engine is more than 15:1, stoichiometric air fuel ratio, that means chemically correct air fuel ratio. Let us say chemically correct air fuel ratio is 15:1, let it be. If I write the air fuel ratio 10:1, this is coming under rich mixture. Here chemically correct air fuel ratio is 15:1 means for burning one particle of the petrol, 15 particles of air is mixing. That means if I supply 15 grams of air, 1 gram of petrol can be completely burned. That is the meaning of chemically correct air fuel ratio or stoichiometric air fuel ratio. Since 15 grams of air particles are required for burning 1 gram of the petrol, if I supply or if I maintain air fuel ratio 10:1, only 10 grams of air is available for burning the 1 gram of petrol. That means air is insufficient. Because of the insufficient, complete combustion cannot be possible. Of course, this kind of mixture is called rich mixture. Rich mixture. In the rich mixture, the amount of air which is required is less than sufficient, therefore complete combustion cannot be possible. Whereas if I maintain the air fuel ratio more than 15, let it be 17:1, I am supplying more air particles for the same quantity of the air. For the same quantity of petrol, I am supplying more quantity of the air for the same quantity of petrol. Means more than sufficient quantity of air is available or more than sufficient quantity of oxygen with air available. Therefore, complete combustion can be possible. If the fuel is completely burned, the representation C plus O2, fuels are mainly having the carbon and hydrogen. Carbon is reacting with oxygen to produce carbon dioxide. It is the representation of complete combustion. But if I maintain the rich mixture, because of the insufficient oxygen present in the insufficient air, the carbon may not be completely reacting with oxygen to produce carbon dioxide, then carbon monoxide may be produced. Anyhow, this kind of mixture I can say lean mixture. Lean mixture means the amount of air what we are allowing for the combustion chamber is more than the required level. That means if the air fuel ratio is more than this quantity, that is called a lean mixture. With lean mixture, complete combustion can be possible. If the air fuel ratio less than this value, that is called rich mixture. Rich mixture means the amount of air allowed for the combustion chamber is less than sufficient, therefore complete combustion cannot be possible. Because of the incomplete combustion, the combustion products are maintaining carbon monoxide. Anyhow, it is given for if the air fuel ratio of the mixture in the petrol engine is more than 15, NOx is reduced, carbon dioxide is reduced, HC is reduced, carbon monoxide is reduced. Because of the sufficient quantity of the oxygen available with more quantity of the air with lean mixture, the formation of carbon monoxide is less. Chance of carbon monoxide in the combustion process is less. I hope all of you clearly understood. Understood or not? Yes. Then look at the next one. BHP of diesel engine can be increased by increasing the pressure of the intake air, increasing the temperature of the intake air, increasing the density of the intake air, decreasing the density of intake air. As you know, the density is proportional to pressure. When the pressure is increasing, definitely density increases. Next, mass flow rate is proportional to density. Higher the density, higher will be the mass flow rate. When the density is more, definitely mass flow rate increases. Then the horsepower, brake horsepower is proportional to amount of material entering into the system. When mass flow rate increases, definitely BHP increases. He is asking, BHP of diesel engine can be increased by increasing the pressure and increasing the density. Increasing the pressure of intake air, A correct. Increasing the temperature, increasing the density of the intake air, right, also correct. When the pressure is increasing, definitely density increases. Because of the increase in density, more quantity of the air can be, more quantity of the charge can be entering into cylinder. That more quantity of the charge, right, causing for developing the more power. Therefore, you can opt the A and C. A and C are absolutely correct. Okay, na? Similarly, look at the next one. It is asking like this: alcohols are unsuitable as diesel engine fuels because alcohols are maintaining very less cetane number. When cetane number is less, very less, right, the combustion cannot be proceeding, because in case of diesel engines, the combustion has to be taken place because of high compressed or high temperature of the compressed air only. Because of the low cetane number for the alcohols, if I use the alcohol for diesel engine, the combustion cannot be properly happening. Anyhow, look at the option A. The cetane number of alcohol fuels is very low, which prevents their ignition by compression. Option A itself is absolutely correct. Dear friends, as you know, in case of diesel engine, because of only compression, the firing is going to happen. For that we are maintaining large compression ratio. When you maintain the compression ratio high for diesel engine, the temperature after compression is high. That high temperature is causing for that high temperature, that is the temperature after compression is high. That high temperature of the air is causing for combusting the fuel. That's why diesel engine is also called compression ignition engine. But in case of petrol engine, external electric spark mechanism, that is spark plug mechanism, is used for initiating the combustion. Anyhow, alcohols cannot be used as a diesel engine fuels because they are maintaining low cetane number. When the cetane number is low, right, combustion cannot be starting with the high temperature of the compressed air. Okay, that is the option. Similarly, look at the other one. Brake thermal efficiency of the three basic type of reciprocating engines commonly used in a road vehicles are given in the increasing order. Dear friends, remember, the petrol engines are available as 2-stroke engines and 4-stroke engines. Similarly, diesel engines are available as 2-stroke engines and 4-stroke engines. If you compare the petrol engine and diesel engine, definitely diesel engine is maintaining better efficiency. Once again, if you compare the petrol engine and diesel engine is maintaining better efficiency. On the other hand, if you compare the 2-stroke engines and 4-stroke engines, definitely 4-stroke engines are maintaining better performance. Then the order of efficiency is efficiency maintained by 4-stroke diesel engine is more than efficiency maintained by 4-stroke petrol engine is more than efficiency maintained by 2-stroke diesel engine is more than efficiency maintained by 2-stroke petrol engine. That is the efficiency order, right? That is the decrease in order of efficiency. Now it is asking brake thermal efficiency of three basic types of reciprocating engines commonly used in road vehicles are given in the increasing order. Increasing order is 2-stroke SI engines, 4-stroke SI engines, 4-stroke CI engines. Increasing order looking correct. 2-stroke SI engines, 2-stroke petrol engines, 4-stroke SI engines, yes, increasing order, and 4-stroke CI engines. Absolutely correct. Option A itself is correct. 2-stroke SI engines, 4-stroke CI engines, 4-stroke 4-stroke SI engine efficiency less than 4-stroke CI engine efficiency. 4-stroke SI engines Two-stroke engines are always maintaining less efficient than four-stroke engines. Four-stroke CA engine, four-stroke SI engine. No, the four-stroke SI engine is maintaining better efficiency than the four-stroke CA engine is maintaining better efficiency than four-stroke SI engine. Anyhow, option A, absolutely correct. Okay. Similarly, look at the next one. Knocking tendency in SI engine, spark ignition engine, reduces with increasing compression ratio. The knocking tendency in SI engine reduces with increasing compression. No, when compression ratio increases, knocking tendency increases. Wall temperature when wall temperature increases, cylinder wall temperature increases, knocking tendency increases. Supercharging should not be used for the SI engines. By increasing the speed of the engine, knocking tendency can be reduced. Knocking tendency can be reduced by, right, increasing the engine speed, right. Option D can be selected. Okay. Similarly, look at the other one. An IC engine has a bore and stroke 2 units. Internal diameter D equal to 2 units. Stroke length, piston displacement length also 2 units. 2 units. Okay. 2 units each. The area to calculate heat loss can be taken as for the reciprocating heat engine. For the reciprocating heat engine, this is the piston, right. Here the heat transfer areas, let me mark it clearly. Inside the cylinder, combustion is happening. Because of the combustion of the fuel, inside the cylinder, because of the combustion, heat can be transferred to cylinder cover and piston surface, top surface of the piston. The heat transfer area equal to area of the cylinder cover plus area of the piston surface plus heat can be transferred to cylinder walls also, plus area of the cylinder walls. Area of the cylinder cover pi/4 into d square plus area of the piston also pi/4 d square plus cylinder wall area, surface area pi dl. Okay. It is equal to, alright, it is equal to pi/4 d square. Look at the d itself is 2 square plus pi/4 d 2 square plus pi into d2, L also 2, stroke length is 2. Okay. Then this 4 cancelled, pi plus pi 2 pi plus 4 pi. It is equal to 6 pi, that is the heat transfer area, 6 pi units. Option C is absolutely correct. Understood clearly? Yes. Then look at the another question asking like this. An air breathing aircraft is flying at an altitude where the air density is half of the value that at the ground level. Density of the air at an altitude equal to half of the density at the ground level. That condition is given. Okay. With reference to ground level, the air fuel ratio at this altitude is, as you know, the air fuel ratio at an altitude dividing by air fuel ratio at the ground level is equal to root over density of the air at an altitude divided by density of the air at the ground level. It is equal to root over density of the air at altitude is rho GL divided by 2 rho GL. Rho GL part is cancelled. Finally, it is equal to 1 by root 2. 1 by root 2. Therefore, air fuel ratio at an altitude is equal to 1 by root 2 times the air fuel ratio at the ground level. That is the answer. So, with reference to ground level, the air fuel ratio at this altitude will be 1 by root 2 times the air fuel ratio at the ground level. Therefore, option B can be selected. Option B is absolutely correct. Okay, na? Understood clearly? Yes. Now, look at the last question. Last question asked for the silencer. The silencer of internal combustion engine. Silencer is used for, right, reducing the noise. If if there is a big pipe at the exit side of the engine for carrying the exhaust gases, if you make a hole, if you make different holes for the silencer, big sound, sound, that kind of sound is available, right? Anyhow, as a fashion these days, the students are making number of holes for the silencer for disturbing the surroundings. Anyhow, the silencer of an internal combustion engine is for reducing the noise. Noise can be reduced by using the silencer. Without silencer, right, the surroundings are suffered by big noise. Anyhow, option A is absolutely correct. With this, IC engine questions also completed. I hope all of you clearly understood. Understood or not? Yes. Thank you. Thank you very much.